Hello, everybody, and welcome to this second day of the Global Symposium on Recent Advancement and the Way Forward to Confined Masonry Construction Practice. I'm just to let you know that we will start in a minute or so. Dr. Asana Paramalvatteri will introduce the sessions today. We are just waiting to give another couple of minutes to give the participants the opportunity to properly log in. We have a packed program today as well, so we will ask all the speakers to try to keep to the scheduled time so that we can have and we can devote space to the question and answer and the discussion in the panel sessions. In terms of question and answer, please use the Q&A facilities that you can find at the bottom of your Zoom window to log your questions, and we will try to answer them during the session in writing, or we will bring them forward for the general discussions at the end of each session. You can also raise your hand if you have a burning question that you want to ask. And other than that, we shall be very grateful if you can put your name and institutions in the chat and just introduce yourself with your expertise and why you're joining this symposium today. Thank you very much, and I pass the word to Dr. Asana Paramalvatteri.
Hello, everyone. Thank you again for joining today. I think it's 1 minute. We hope you had an interesting session yesterday. It was very engaging, both from the speakers and the audience engagement. Please continue to have this engagement going for this day too. Thank you very much for all the inputs that you have provided yesterday, and we are trying to gather them as we speak today as well. And welcome to the Global Symposium on Recent Advancements and Way Forward in Confined Masonry Construction. And today's talk, we are going to look a bit into the retrofitting and adaptation of existing confined masonry and masonry structures. We have Professor Sergio Alcocer and Sophia Andre and Tim Hart speaking on these three topics in the first session. We have a Q&A to follow, following which we'll have a slightly different topic of discussion, which will be on the durability and climate adaptation of confined masonry construction from Sebastian and Anna. We will have speaker introductions just before each of these sessions, so I'm not going to spend the time now. And after the coffee break, we hope to have much more discussions as we did yesterday. First, we have a panel of reactors to give us their views on what we have been discussing throughout the symposium and from their own experiences in their respective countries. Following which we would open the floor for open discussion. We hope this will be a session that brings together all of the discussions from yesterday and today. Please feel free to open your cameras and participate in the discussion, all the speakers from yesterday and including the speakers and reactors from today. And we also invite the audience, if you wish to share your views in this discussion and ask questions, you're very welcome to do this. And we hope to close not later than 4 p.m. Thank you very much. And just to introduce the panel discussion, as I mentioned, we would try to come up with key messages that are the outcomes of this symposium on standardization, the research needs and resource and knowledge exchange, and in terms of global expansion. Thank you to all the moderators from yesterday and today for taking up this additional role for the symposium. Just to recap the main points that we discussed yesterday, we're very grateful to Professor Svetlana for giving us a very good overview of the design codes and their status in terms of where we stand from Latin America to Europe and the Asian context, and what are the recent releases and the ongoing efforts, and more importantly, the areas that need further improvement in terms of the development, such as the walls with openings and out-of-plane collapse modes. Following which we saw the advancements in numerical modeling and experimental findings. Very interesting to see that these are advancing and augmenting our development of the codes. Then we had a session dedicated to the schools, where we had experiences being shared from different countries, varying from finding the existing deficiencies and then finding ways to retrofit them, with successful examples of such retrofit cases. And also, it was very interesting to see the variation of these typology between the countries, and to which context the global taxonomy, the GLOSI taxonomy, could be a very good addition and contribution to characterize common buildings and then have seismic assessments. And one thing that emerged through the panel discussions also was the need for certain guidance in terms of school construction using confined masonry. We also had this interesting discussion on CM, confined masonry as a dual systems, or the advantages or the possibilities of expanding it to a hybrid construction, especially when we have the requirements of large openings and spans. So in conjunction with the school discussion, I'm hoping that we could take this idea forward as we have the discussions today, and hopefully further in the future. And regarding a short discussion on the walls with openings, it's great to see that this is a topic of relevance, and it's been addressed by several research communities. Hopefully we'll have more refined guidance regarding this. And there was also this discussion about disseminating the knowledge that we have already existing in certain countries regarding the school construction and retrofitting, while it's not just the guidelines or the existence of them, but also the need for strict site management, as pointed out by some of our panelists, and the need for educating the system, educating the new engineers and the authorities regarding this typology in general. So with that as a backdrop, we will move into today's discussions, and hopefully we will have some outcomes by the end of the session. Just to give an idea of what we plan to do with these points, we are, as we initially mentioned, we are planning to produce a white paper as with the objective of compiling the discussions to identify the gaps in research and standardization, and what we can do further to advance this technology all over the world. So this we will request all the speakers and reactors to contribute by about 1,000 words write-up in respective topics that you have presented, but also addressing the questions that are being raised in this symposium. It would be really good to have this as a write-up, as a compiled version of all of these discussions we have here. And it's also open to all our participants. It would be really great if you could share your views as well from your own country's experience of confined masonry construction, or the retrofitting, or the construction of schools in confined masonry, and so on. We hope that we receive these write-ups by the next week, so that we can then start working on this and produce it as a paper. And regarding the resources that we plan to share after the sessions, we will definitely have these recordings shared with you, with all the participants, and it will be available freely on the UNESCO Share website. This is the link here, which you can come back and visit the recordings later on. And we also are planning to compile all the PDF presentations that are being presented here, which will also be made available to only the participants. And regarding the resources that Professor Svetlana mentioned, we have a repository of several design codes and guides from these countries. And she's very kind to share this with us so that all our participants can access them and may be used for their respective purposes. And if you wish to contribute to this folder, please let us know. And if the documents are free to be shared, we will definitely add this to the folder. And this will also be shared with you as in an email after the event. And thirdly, as I mentioned, we have this white paper in plan. So we are also sharing this with all participants, and also after it's published, it will be freely available. And we appreciate if you could also circulate this in your networks and with your colleagues. I think that's all just to begin the day. I will now introduce our speakers, the first speakers for the first session. Professor Sergio Alcocer, professor at Institute of Engineering, UNAM, and Sophia Andrade from Build Change, lead engineer for Columbia, and Tim Hart, senior advisor engineering at Build Change. If you could provide a bit more introduction of your own work in your words, that will be much better than me reading out your bios here. Thank you very much, and I invite Professor Sergio Alcocer to take the stage. Thank you.
Good morning, everyone. At least good morning from Mexico City, good afternoon, or good evening in many of the places in which we are. It is my distinct pleasure for me to be with you. I would like to thank Professor Dayala for inviting me to share some thoughts about the retrofitting of confined masonry structures. And thank you very much to Asana for putting together this very interesting symposium. And I would like also to thank her. So I would like to start by presenting my group, Diana Ramirez. She's a master's student at the National University of Mexico. And we have been working for many years. I started working at the university in 1991. And since then, I started working on confined masonry. I haven't done it experimentally in recent times, but I've been working mostly now on issues related to retrofitting on confined masonry. But before talking about confined masonry, we need to understand why we need to retrofit a structure. In many cases, we have a structure that is being damaged, whether structurally or non-structurally, and could be related to earthquakes or many other actions. In some other cases, we need to retrofit the structure because of the change of use on occupancy, because we are modifying the building that has some impact on structure, because we're changing the loads. In other cases, we need to rehabilitate the structures because our codes will order the rehabilitation of the structures. And in many other cases, which are very rare, the owners may decide to improve the behavior of the structure. And this typically happens after an earthquake, when they see that their building is similar to others that suffer damage, that collapsed even. And in those cases, the owners of those structures may think that it's proper to actually rehabilitate or strengthen the structure. So now that we are talking about community resilience, retrofitting becomes a very suitable strategy, very significant strategy in many countries. Of course, for some countries, in order to achieve resiliency of existing structures, its demolition and the building of new structure may be relevant. But in many other countries, that really is not possible, just because of the availability of resources. So retrofitting becomes a very significant strategy, of course, always with a cost-benefit analysis behind it, so that we maintain the replacement cost to a reasonable level. Of course, reasonable level is different in countries, in advanced economies like in Japan or in the United States, and it's quite different in other emerging economies, for example, in Indonesia or in Mexico. So those replacement costs are quite different. And of course, one of the things that we have been looking into when we retrofit a structure, or when we design a new structure, retrofit a structure, is attaining a functional recovery performance level. At least in Latin America, confined masonry is one of the systems that is very widely used. At least 70%, in the case in Mexico, of the construction is being made through confined masonry. That means that either we use handmade units or we use industrialized units. And confined masonry is very relevant because of its simplicity in construction. People, masons, know very well how to construct confined masonry. In many cases, of course, with areas of opportunity for improving the quality of construction. In Mexico, we suffered a couple of earthquakes in 2017, one magnitude 8.2, the other one magnitude 7.5. But the one that really kept us of our attention was the one that was close to Mexico City, in which over 1,000 buildings had to be rehabilitated. We worked with the University of Texas at Austin, with the government in Mexico, in order to develop an inventory of over 200 structures that were rehabilitated after this earthquake. And we found, as you can see on the right-hand side in this chart, the prevalence of the different techniques used for rehabilitating structure. And one of the techniques that were most widely used was the use of welded wire meshes attached to the masonry wall.
Sorry to interrupt you, Sergio, but we don't see your slides progressing. We are still on slide 1. So I don't know if that was by design or there is a problem.
No, it is not by design. Let me go back to this. Do you see now?
Now we see the speaker's presentation.
Okay. So
not the.
There you go. I think this is the one, right?
Let's see. At the moment, has not come through yet. Can you try again?
Yes.
Yeah, now something. We are as it was before, and we are on the first slide. Maybe you can automatically progress it, or just.
Yeah, the problem with what I have is I have these 3 monitors, and it's always a problem to come up with the one that you need to. It should be this one here. Let me try this one. Now, do you see? What do you see?
We see slide 1.
Wow.
If you don't mind that we see the speaker, then yeah, now we can see slide 2, but
okay.
You need to progress them one by one, basically.
Okay, I'll do that.
Yeah.
So this is what I was showing before, which is the number of buildings that were rehabilitated in Mexico City due to the 2017 earthquake. And as you can see, there are many techniques that were very widely used. For example, adding reinforced concrete walls, steel braces, and column jacketing for concrete jacketing columns. But one of the techniques that were widely used for masonry structure was the addition of a jacket or a thickness of the wall reinforced with the welded wire meshes and covered with cement mortar. So what we have been doing in recent times with the help of Diana Ramirez is studying other different techniques in order to understand their behavior and trying to come up with a reasonable design approach for all these techniques. Of course, we started with jacketing with welded wire meshes, as I mentioned, but there are other techniques that have been tested in the laboratory and in many cases have been used in the field. Some of these are jacketing or addition of steel bands, as you see in the middle of the slide. Also jacketing with the polypropylene band meshes, which is a very simple and very inexpensive method, or jacketing with steel plates. You see here with the small charts, the relative cost and the ease of construction, the facility, how easy it is to construct these different techniques. We also looked at jacketing with the fiber reinforced polymers, particularly these are carbon fibers, although glass fibers have been used. Fiber reinforced mortar jacketing and jacketing with this textile reinforced mortar. These are techniques are available in different countries, and as I said, they have been tested in the laboratory. In order to better understand the performance of these techniques, a data set was assembled with 94 specimens. You can read here the fields and the data set that we assembled, general information of the research project, and then all the way to the experimental results that were presented by the authors whether in articles, in papers, or in thesis of different students. Where Diana is working right now to upload the database in the website Design Saved, and so that it can be used. It can be downloaded freely if someone is interested in doing it. From this experimental database, we found very interesting things. First of all, is that most of the research that has been conducted is on welded wire meshes, about 40% of the research, 28% on steel bands, and the remainder 18% with FRP bands. Then you have a little bit of distribution here with a small number of specimens tested for the other types of techniques. So the one thing that is apparent here is that there are pretty much three techniques that have been most widely tested: welded wire meshes, steel bands, and then FRP bands. Most of the tests has been conducted on confined masonry and on reinforced masonry, and particularly in masonry infill walls. And whether there is some other research being conducted on reinforced masonry itself and load bearing on reinforced masonry walls, but mostly it's on infill walls and confined masonry. Then what happened here? Then we also see what type of units were used in the walls that were tested. And as you can see here, pretty much 50% of the tests have been conducted on solid clay bricks. This is the typical brick available in different countries. Is the first one here on the left-hand side and the lower part of the slide. These are mostly handmade units. 29% had been done in hollow clay bricks, they're like the ones on the right-hand side, and the remainder with different types of units. Most of the tests have been conducted on walls that either are square or that have squat walls that are prone to exhibit shear failure. And the main reason for this, of course, has to do that these techniques have been tested in order to preclude the shear failure of confined masonry walls. We looked at the different equations that either authors have proposed or they are available in the literature. These could be equations in codes or equations in different papers. And we use these equations in order to normalize the strengths that were measured during the tests that were reported and are included in our database. From these, we derived different performance curves similar to the ASCE 41 approach in order to come up with the backbone curves for each of the specimens for each of the tests. We identified the onset of cracking, the maximum strength, and then the ultimate strength, considering ultimate strength to be 80% of the maximum strength. We looked at different parameters in order to understand and to actually divide the universe of the tests that we had available, particularly depending on the failure mode. Not all tests failed in shear. We have different types of failure, and of course, we couldn't compare one to the other one. There are different failure modes, and we need to understand that. We also looked at the structural configuration, particularly the type of masonry that we are dealing with, the type of unit, the aspect ratio, and whether the structure had previous damage or not. Some of the tests that we have in the database means or comes from specimens that were tested before and then were repaired using one of these techniques. So we looked at one model that was developed by Professor Riahi, Professor Elwood, when both of them were in Canada, and myself. This is a development that was published in 2009. And this was the first attempt to develop a backbone curve for performance-based design for confined masonry. At the time, we assembled a database of the information available at that time, and then we come up with these equations here that with the idea of identifying the performance. As it was presented yesterday, you could see, for example, in the maximum strength equation, that is presented in the similar fashion that was presented by one of the speakers, in which you have the contribution of the masonry, the contribution of the vertical stress, as well as the contribution of the column reinforcement, of the tight column or vertical reinforcement. Of course, you can add the contribution of the horizontal reinforcement, if that would be the case. With this in mind, we came up with these different backbone curves. In purple here is a comparison of the Riahi's equation, which is for confined masonry only. That means tight columns, tight beams, and the masonry itself. Whereas the other columns on the left-hand side are curves that come from welded wire meshes or walls that have been strengthened with welded wire meshes. And you can see the difference in terms of behavior. They are stiffer, of course, because you're adding a layer of mortar. They are stronger, of course, much more stronger than the actual confined masonry structure, and of course it has a much improved deformation capacity because of the addition of the welded wire meshes. The one in orange is an average of the backbone curves and is the one that we are proposing to be used if someone is interested in analyzing structures using performance-based. We are also developing other types of cores, for example, for steel plates in which crushing occurred. You can see that in some of these cases, the dispersion of the results is quite significant, not so as in wire meshes, but this is quite significant in many of these techniques. So we could see that there are very few tests, and in some cases, the dispersion is quite ample. For example, in the polypropylene bands or using FRP bands, you can see again that the tests are very well aligned. Look at that in the y-axis, we have normalized the strength using the equations that I mentioned before, and on the x-axis, we are using drift ratio as a measure for the displacement. And again, as I said, we came up with performance curves, backbone curves that could be used for performance-based design. Of course, I'm not interested for you in reading these tables, just to let you know that we have come with tables in which, depending on the type of masonry, confined masonry, or reinforced masonry, or infill walls, what have you, the types of units, the type of failure, the type of the relative aspect ratio of the walls. You have a set of numbers, a set of values for the drift at cracking, at maximum, at ultimate, and their corresponding strengths, so that you can build up the performance curves, and then you can perform any type of analysis. In some of these cases, because of the lack of information, these should be considered as indicative curves, because we really don't have enough information to actually come up with a reasonable curve. So what conclusions can we make from these experiments and analysis of these experiments is that we have very limited and very variable information in some of these cases. Certainly the most studied technique has been the jacketing with welded wire meshes, which is a very cost-effective technique. But there are others that are very promising and they need to be studied further, like, for example, textile jacketing or the use of fiber reinforced mortars. The use of steel plates give very good results, but their cost is very high, and I'll show you what I'm meaning from that. And then what we have done in terms of performance-based design, we have tried to come up with different sort of families with all these curves that are related to a specific type of masonry and a specific type of a failure mode. And this is the type of curves that can be drawn based on the numbers that I show you in the tables before. As I said, in some cases, I think we have enough information to at least propose a curve. In some other cases, should be only indicative because we don't have enough information. One of the things that we did also was performing an economic analysis based on the cost in Mexico City. Of course, those costs may differ in different countries, of course, but at least it tells you the relative cost of some of these techniques. The cheapest technique is the polypropylene bands. The polypropylene is a very cheap material that could be used very easily in the field. And the second cheapest technique is a welded wire mesh. You can see that compared to the use of steel plates or steel bands, or the use of textile reinforced mortar, carbon fiber, the costs are really quite high. So one of the advantages of welded wire mesh is it's a cost, but also is the performance. I just wanted to stress, for example, the comparison between these two tests that we performed in 1994. That means 30 years ago we did this test. We published them in 1996 for the 11th World Conference on Earthquake Engineering here in Acapulco, in Mexico. And you could see that the difference between a confined masonry wall on the left-hand side and then a wall that had been strengthened with a wire mesh that has an amount of steel that amounted for 0.35 megapascals. That means multiplying the amount of steel by FY typically 6,000 kilograms per square centimeter, 600 megapascals. And as you can see, there is a significant increase both in strength and deformation capacity. The behavior is quite stable. There is a very nice distribution, uniform distribution of cracking throughout the wall. And certainly it improves the behavior, not only of an existing structure, but also for new construction. So in case of structures that need, you need higher strength even for new construction, instead of adding reinforced concrete walls, you could add a wire mesh attached to the masonry wall, and that would increase the strength up to about double or more to what you have from the masonry itself. Things that we have learned is that you need to attach properly the mesh to the masonry. There are different techniques that can be used, either common nails or the use of powder actuated fasteners like the ones in the middle. One thing that we have learned is that you should use standardized materials as much as possible. And one other option that could be used, the meshes for, is if you connect them to the foundation, meshes could be used to strengthen the structure of flexure. This is my last slide. I just wanted to highlight the new document that we produced in Mexico City that was published in last November. Is a 282-page technical standard for the evaluation and rehabilitation of existing structure. It is applicable to masonry, concrete, and steel structures. It has 13 chapters and 2 appendices, and it covers evaluation, analysis, design, detailing, construction, inspection, and quality assurance requirements. That means that you cover the whole spectrum of what you actually need for retrofit a structure. And we have included 14 rehabilitation techniques in detail. That means that for those rehabilitation techniques, you have analysis, design, detailing, construction, and inspection requirements on how to perform those techniques properly. And I just outlined 8 of them that have to do with masonry. A local repair, for example, when you have a tie column that is damaged, what to do with a tie column or tie beam that is damaged. What do you do if you have a cracked wall? How do you repair the wall? In case you need to replace damaged elements, how do you perform that replacement? How do you connect to existing elements? This is a critical issue when you are adding new elements to existing elements. How do you connect them? The welded wire mesh wall jacketing, as I mentioned, addition of new diaphragm walls in many of the frame structures. You need to add new diaphragm walls. It's not the intent of this symposium to talk about diaphragm walls, but I just wanted to include it because these are infill walls. How do you separate walls from the wall parapets from adjacent columns? Yesterday, we saw in many of the schools damage credited to short columns, and this had to do with masonry or concrete walls who are adjacent to the columns that eventually lead to failure of the columns. And the question here is, what do you do when you have these cases? How do you separate wall parapets? And in some other cases, you need to add new tie columns or tie beams because the walls do not have those elements. They are not properly confined. You could read on the orange rectangle here the address in which, if you want to download these standard, of course in Spanish, but it can be useful to many of you. And then finally, I just want again to thank Professor Dayala and Professor Brizev and others for inviting us, and this is where you can find us should you are interested in further information. And I hope I'm on time, Asana. I see you here. You are very anxious. Thank you very much.
Thank you very much, Professor Sergio. This is very interesting, and thank you for all the resources, the additional links, and where we can access them. We will have some time for the Q&A after 3 presentations, so I will right away move forward to invite Sophia. to talk about the Colombia's first national regulation for evaluating and reducing risk in informal masonry housing. Thank you. Sophia, please.
Thank you very much, Oceana. I'm going to share my screen. Please let me know when you're seeing it.
Yes, we can. Yeah, all good.
Okay, perfect. Okay, so thank you very much to all the people here listening to this presentation, and thank you to Professor Alcocer for an outstanding presentation. I'm going to talk about IS 410-23, which is Colombia's first national regulation for evaluating and reducing risk in informal masonry housing. This document was developed by the Colombian Association of Earthquake Engineering in collaboration with Build Change and researchers from different universities, such as Escuela Colombiana de Ingeniería Julio Garavito, Universidad de AFIT, Universidad Militar Nueva Granada, and the whole engineering community. AIS is a non-profit whose traditionally has developed the proposal for regulations in Colombia. And in AIS, we are able to gather different engineers working as designers, builders, researchers, and it is extremely important because with all this knowledge and all this information, we are able to provide regulations that are affordable, but also have taken into account the context that we are working of. Also, I would like to highlight and thank all the members of IS 400 Committee, which is vulnerability and damage assessment, and all their work and all their effort in producing these guidelines are changing the way that we're constructing, in the way that we're facing risk and vulnerability, structural vulnerability problems in Colombia. So I would like to highlight all their work and thank them for producing this document alongside with us. Okay, so I'm going to divide my presentation in different phases. First, I will start talking about who is Build Change and why we are working here. Then I will continue to provide some information about Colombian context and also the regulation context. Then I will talk about what is informal housing and why it's so important to address this problem, and the development of IS 400, the importance of a strong policy in all this development. And finally, I will talk about the challenges that we face, the progress made, and what comes next. I hope the time, I'm not going to go through them. Okay, so first of all, Build Change is a nonprofit, and our mission is to reduce deaths, injuries, and economical losses due to the collapse of houses and schools and during earthquakes, climate-induced events, and also fires. And we do it through a combination of advocacy and awareness raising, policy reform, access to finance, access to information, local capacity building. After 20 years of working in different countries in Latin America and the Caribbean, and also in Asia, we have achieved more than 1 million safer people, more than 230,000 safer buildings, more than 40,000 jobs created, and around 4.75 billion in assets protected. Now, let's talk about Colombian context. So Colombia is part of the Pacific Ring of Fire. We have a hazard map, a seismic hazard map that you can see on the left. And here you're able to see that it is divided in 3 zones. It is high seismic hazard zone, intermediate, and low. The majority of the population in Colombia, around 83%, is located in intermediate and high seismic hazard zone. In the past decades, we have faced 2 disasters, 2 main disasters. It is Popayan earthquake in 1983 and also Armenia earthquake in the Coffee region in 1999. And I have to tell that the problem here is the vulnerability, the structural vulnerability. So considering this and take into account this, AIS, the Colombian Association of Earthquake Engineering, was created around 1975, and they developed at the time some guidelines that were not mandatory. But after the earthquake, the Popayan earthquake, the national government decided to create construction and design regulations that has to be mandatory at the national level. So they contact the Colombian Engineering Society, and the Colombian Engineering Society contact IES to develop the proposal that was then approved by the Code Commission and approved by the Ministry of Housing. This is like the main the regulations developed in the country. Right now, we have NSR 10 regulations, and we are developing the new and the update of these regulations. It is a document called IES 124. It's going to be published this year, and it's going to go through the process of approval for the Code Commission and also for the Ministry of Housing. And even though IES has been working in reducing vulnerability, I have to say that we have achieved it in the formal sector. When I'm talking about formal sector, I'm talking about buildings that were conceived, designed, and also constructed with the assessment of professionals, engineers, and architects, and different professionals of different careers. Quality controls were carried out, and these buildings are not vulnerable. However, when we think about informal housing, the context is completely different. And this is something that it is not for Colombia, it is also for Latin America and the Caribbean region. So we are talking about that around 65% of the existing housing stock has been constructed informally and can be considered vulnerable to hazards. And 65% is the average in the country. In some cities, for example, in Cali metropolitan area, we're talking about 80% of the houses. These type of structures can be classified as load-bearing masonry systems, the majority of them. We also are able to find in the informal housing houses made by using earth materials, using also bamboo and wood, but the majority of them are classified as load-bearing masonry systems. Can be classified also as unreinforced, partially confined, or confined, and they are constructed using brittle and weak clay or concrete units and cement mortar. It's important to say that they present different structural deficiencies and are built and expanded progressively over time. And when build changes start working in the region, we start working in Haiti, and then we start moving and also in Central America, and we came to Colombia in 2014. And at the beginning, when we saw the problem and the magnitude of the informal housing in Colombia, we decided to start working right here with the national and local governments to reduce vulnerability at scale. However, when we start working on this, implementing and using NSR regulations was not practical at all, because NSR regulations were developed thinking in the formal sector, not thinking in the informal sector. That is why we start developing a manual for retrofitting informal housing. And by doing this, we had to use different codes as ASCE 31 and 41, plus including a specification from NSR regulations. This manual was approved by the Code Commission. It could be applied at the time only by build change engineers, and that was not our goal. We wanted to be applied for every engineer in the country. In this manual, we were able to introduce an alternative methodology, taking into account that we want to strengthen considering the real informal materials used in these type of neighborhoods. We also include the construction quality, that it is average or bad, and we include also realistic geometrical characteristics typical of this type of construction. Then IES contacted us and asked us if we wanted to be involved in IES 400 committee for developing a regulation that could be applied at the national level. Of course, we say yes, and we start working with different professionals, researchers, builders, also professionals involved in the permitting and the process of permitting in Colombia and with the entities that provide the construction permits. And we were able to develop this document. Of course, it is not perfect, it is a work in process. And I want to highlight how we are applying this and providing some examples of this application. So I wanted to highlight that real field samples were tested. This is extremely important because we are not using the materials with the specifications of NSR regulations. We are using third quality materials that can be found in the neighborhoods. So of course, we characterize the materials and also perform full-scale tests. And as a result, we have a regulation that it is framed in NSR regulations, also in regulations from other countries and build change manual, and considers the law and decrees that regulate construction and the permitting process by dedicated offices in Colombia. Also, we have a document that considers the reality of housing on informal housing in Colombia and presents an evaluation and designs methods specifically for these type of structures. And of course, it collects results from experimental carried out in carried out in informal masonry. Okay, so how is the flow chart? First, we start with a preliminary information. We have to collect and gather all the preliminary information before decide to intervene a house. We have to check all the territorial development plan for each location and look at the hazard maps and establish the legal feasibility of the interventions. Then we continue with the building evaluation. We do it house by house on field. We fill out an evaluation checklist, and this is extremely important. Engineers might need to use their best criteria to define some assumptions, because in the informal housing, we're going to find so many different scenarios, and the best criteria has to be used. That's why training is fundamental. We identify the deficiencies in each house, and we establish the feasibility of intervention using the document. Then we continue with the design of the intervention. So we have to provide a proposal for the existing deficiencies, how we are going to intervene these existing deficiencies. We use the seismic demand provided by NSR regulations, and also we have some information of microzoning. And we have to come up with sustainable solutions that are locally appropriate. We need to come up with solutions that can be that are affordable and can be used in the territory. It's extremely important to train builders and homeowners, and we use standard construction details with prescriptive solutions for developing the design package. The following stage is the permitting, getting the permits for the construction and the construction phase. Okay, so how we are tackling and how we are reducing the vulnerability. So our strategy is to, of course, increase the strength, the shear strength of the walls, and also reducing the demand, the seismic demand. So on one side, we are using and jacketing with wire mesh. We call it mesh plaster, putting mesh plaster in some of the walls, strategically considering the configuration, also constructing new walls. And on the other hand, we can change the structural system. We classified most of these houses as unreinforced masonry, but we can change the structural system to confined masonry. And you can see here in the picture on the right, that here you have a new wall constructed considering the configuration of the house, but also an existing one with a tie column that we are using to transform the structural system. In the foundation, it is common for us to find beams in the perimeter of the houses, but it is not common to find it internally. So we have to build and construct in order to create rings in the foundation, and then continue with the construction process. Okay, continuing with this, so we can change the structural system to confined masonry, which is one of our main solutions, but also we can find strategies to reduce the dead load in the house. For example, changing some of the non-structural walls for lightweighted ones, and we found different strategies so we can retrofit the houses. Okay, so right now let's talk about the progress made. We were able to contextualize the problem. And this is something extremely important because 2 decades ago, informal housing was a topic that just a few engineers were talking about. And now, right now, it's a trendy topic in the country. We were able to develop a document with pertinent guidelines and recommendations for reducing the vulnerability in informal masonry houses, thinking within the framework of the local and national legal regulations. We were able to adjust experiences of several local universities, and we were able also to generate recommendations with the limits framed in the best criteria of the responsible engineer and designer. And we were able to include a progressive approach. And I'm going to talk about it with the importance of having strong policies and impacting the public policy. So in Build Change, we apply constantly a theory of change. In this theory of change, we want to create a change in the systems, and we want to have an impact over time. In this theory of change, we have 3 strategic pillars, which are P, M, and T. P is related with people, government, residents, funders, and here we have also public policy, impacting public policy. In T, we have technology, which is having and providing our guidelines, having more information about this, also including and using technological tools. And then we have money, which is how we are going to finance this. So in the national government, I'm going to take just 2 seconds to finish. In the national government, we have in Colombia home improvement programs that are subsidized. And the majority of them have been done only with habitability purposes. Right now, the present government includes some structural categories that are not implemented yet. However, the first step was to develop the regulations so we were able to start creating the pathway to develop and to perform and to use these categories at the national level. So having this document, this regulation, is just one of the first steps to be able to reduce vulnerability at scale in the informal housing. And that's why a progressive approach is important, because we have a maximum amount of the subsidy, and as you can see here in the table, for urban and rural context. So we have a maximum amount of subsidy, and we have to perform and decide which activities are going to be done. So a progressive approach is fundamental, and we were able to include it. Challenges, many. Of course, it's a work in progress. We need to continue including new strategies and new ways to retrofit this type of structure that are affordable and also locally appropriate. And for next steps, the second version of the ICE regulation, defining the structural categories in the home improvement programs at the national level. And also in Colombia, it's been developing right now the National Seismic Risk Model. And we want to continue working with all the entities involved in this process to defining the activities that can be done and which one of them is going to reduce the most the vulnerability in this type of structures. So thank you very much to all. If you want to know more about the things that we have developed in ICE, I will be thrilled to contact you and put you in contact with ICE for Handling Committee. And also, if you want to learn more about what we are doing in Build Change, of course, you can contact me as well. So thank you very much.
Hi, Sophia. Thank you. Thank you very much. And thank you for keeping the time. We can move on to the next presentation. I think there are some questions for you, Sophia, in the Q&A, if you could have a look. Thank you. Next, I would invite Tim Hart to talk about the application of confined masonry in post-earthquake housing reconstruction. Tim Hart is working as an engineering advisor at Build Change. Thank you.
Thank you, Ashana. And hello, everyone. And I'm honored to be asked to present at this presentation to all of you. So I'll be talking for the next several minutes about the application of confined masonry, primarily in the post-earthquake reconstruction environment. So hopefully you can all see it. So when we're talking about
Yes, Tim, go ahead.
Thank you. So when we're talking about implementation in confined masonry, where it has several different aspects to it. One is new construction, primarily reconstruction after an event, which is pretty standard, of course. And then, as Professor Alcacer referred to this morning, oftentimes a major event will trigger a desire or a need to strengthen or retrofit existing construction, both confined masonry as well as retrofitting of existing framed infill or unreinforced masonry constructions to confined masonry. So all of these are involved in a post-event reconstruction environment. Additions and renovations is not something that is typically considered initially in these environments. However, it is something that definitely needs to be taken into consideration for long-term applicability, long-term sustainability of this, because whatever you end up building is going to be renovated. It's going to be added on to at some point, and so whatever we do with these buildings need to be able to accommodate all of that. So the conditions that we typically run into generally fall into three buckets. One is where confined masonry is well established, like in Mexico and Peru, where it is a very common construction type. It is used for commercial and residential, for many different types of structures. And there are codes and standards that are well established and typically well followed. Then you get into the situations like we have in Indonesia and Haiti and some other locations where the confined masonry it's informal construction. It is very commonly done, but it is not commonly used for commercial buildings. It is used typically for residential, also for schools, as we learned yesterday. Codes and standards for confined masonry either don't exist or are still in development. There may be guidelines available to help with the construction, with designing and building these buildings, but it's not a codified, it's not a standardized system. And then you also have environments like in Nepal and in India, where confined masonry is relatively new. It is not a common construction type. It is where there are standards, either they don't exist at all, or as in the case of India, they're just recently being introduced. So in that situation, you're dealing with a very, having to train people on what confined masonry is and how it's different from, say, framed infill or unreinforced masonry. So all of these environments have different conditions, have different things, different parameters that we got to deal with. I'll be mostly talking about the environment for informal construction because that's where most of our experience has been in. Beginning in Indonesia, where I began work with Build Change back in 2005 after the earthquake and tsunami in Banda Aceh. So confined masonry is very commonly used for building for housing. Primarily for housing. It is also used for schools, more so on Sumatra and some of the and Java on the western side of the country as opposed to the eastern side, but it is common throughout the country. It does have some significant differences from confined masonry as used in other countries. The most significant, which is the walls, which are very tall and very thin because of in Indonesia, you can't thicken the walls. They're all single width walls. So as a result, you now get walls with very high thickness ratios, typically getting up around 30, when the maximum height thickness ratios you typically see is around 15 to 25. So we're dealing with a very relatively unique situation here. Tall masonry gable walls are also very commonly used. Because the walls are so thin, so are the tie beams and the tie columns. Typically, in most countries, you'll see tie columns around 20 to 25 centimeters. In Indonesia, they're typically 10 to 15. And that's, again, because of the way the walls are built. And as a result of these differences, as a result of these unique conditions, the standards that have been developed for other countries can't really be applied directly to construction in Indonesia. And as I mentioned before, there are no codes or standards for confined masonry in Indonesia. So moving on to Haiti, like Indonesia, it is a very common type of construction used for housing. Unlike Indonesia, where there are codes and standards, though not for confined masonry, in Haiti there's nothing. Basically, all construction in Haiti is informal construction, so it's basically a wide open situation. The concrete, the masonry that is typically used in Haiti is hollow concrete block, typically without reinforcement. Vertical expansion is, because land is so valuable there and so limited. Vertical expansion is very common. So you have to, if you're designing a new house, you have to make sure the design accommodates multiple floors, even if they don't build all of them right away. The hillsides there are very prone to landslides. A lot of deforestation has occurred there. So there's a lot, there's this landslide issue. And in addition to earthquakes, you're also dealing with hurricanes that in part forces on the walls that are, unlike Indonesia, which does not have hurricanes. There are hurricanes, and they have to deal with hurricane force winds in Haiti. Likewise in the Philippines. So in the Philippines, there's some similarities to Haiti in that they also use hollow concrete blocks. They also have to deal with typhoons. In fact, some of the highest typhoon loads in the world occur in the Philippines. The type of confined masonry construction they use there is kind of a hybrid system. It's not a pure concrete or a pure confined masonry system, in that the columns are typically poured first before the walls are built, and then the beams are poured after the walls are built. So it's kind of a sort of confined masonry. They do typically reinforce the masonry there, unlike in most places. Multi-story houses is very common in Metro Manila and other urban areas. But once you get into the rural areas, it's more single-story, single-family residences. Like Indonesia, it's a very hot, very humid climate, so there's a lot of openings for ventilation. There's very tall walls, particularly tall gable walls. The roofs are typically light framed. So a lot of some of the provisions that exist for guidelines for confined masonry are primarily assume concrete slab floors and concrete slab roofs, which they don't typically use in the Philippines. And then going to a situation like reconstruction in Nepal after the earthquake there. In Nepal, confined masonry is not commonly used. Typically, they'll use a stone masonry in the rural areas, like you see on the photo on the right. In Kathmandu, in the urban areas, it's more common to see reinforced concrete frame with infill or unreinforced masonry. So confined masonry is a new technology there. The walls there typically have many openings. A lot of that is due to the fact that these houses also serve as businesses for many of the people who live there. So they need a lot of openings to conduct their businesses or to do farming, storage, and things like that. The walls are very thick stone masonry. The roofs, however, are very light, typically light framed with either timber or light gauge steel. And accessibility and particularly in the rural areas is very, very difficult. You can see the photo on the right. That's kind of a standard roadway, major roadway to get to some of the rural villages in Nepal. They're very steep. They're very narrow. So you can't get trucks up there. You can't get a concrete truck up there. So importing materials gets very costly. And in some cases, particularly during monsoon season, it's next to impossible. In addition to that, the labor force that you see is typically confined within the villages. The people who do the building in the villages are people who grew up there, who were born there, who never leave there, and then they just train the next generation. So that it's very, very confined and very isolated environment that we're dealing with here in Nepal. Even though there are many differences in how confined masonry and how construction in general is done, there are some common challenges when trying to implement confined masonry in these environments. One is that there is often no codes or standards for confined masonry, or in the case of Haiti, no code for anything. There are guidelines that exist in some countries, like Professor Bowen, Teddy Bowen, guidelines for Indonesia, which were very helpful for us in the very beginning. And there are other countries that have similar guidelines that are useful. The masonry units that you typically see, either whether they're clay brick or concrete block, are typically handmade. They're typically low quality. In Indonesia, for example, the standard calls for 5 megapascal compressive strength for clay bricks, but you typically see bricks with about half that capacity. The reinforcement details are very weak, generally speaking. The stirrups have small hooks. The longitudinal reinforcements have even smaller hooks. The stirrups are not spaced properly. Sometimes non-deformed bars are used. That's a very common thing that occurs in many of these places. When you're dealing with housing construction, that's oftentimes done without the use of heavy equipment. You don't see mixers, concrete mixers. You don't see concrete trucks on these sites. So a lot of it is concrete's mixed by hand. The bricks are made by hand and placed by hand. It's all very informal. And then there is a general lack of experience with, in some cases, lack of experience with confined masonry. In other cases, is lack of experience with quality confined masonry. The builders don't really know how to build these things properly. And there's no established construction quality assurance programs. You don't see building officials, you don't see special inspectors, you don't see testing of rebar or testing of concrete. You don't see any of that. It's all very informal. And depending on the environment, there are limited financial resources. After major disasters, you'll see large organizations and as well as governments provide money to homeowners to rebuild and reconstruct. But in smaller events, those resources generally are not there. And so the homeowners themselves, who do not have a lot of money, are now the ones being asked to pay for all of this. So some of the things that bill change has done over the years to address these, I'll talk about these now, beginning with new construction. So we've adapted confined masonry, the best practices of confined masonry that we've been learning these over the years. When we first started this, nobody really knew what confined masonry was or how it behaved. There wasn't a whole lot of literature out there. Now there's a lot more. And so there's a lot more that can be, a lot more best practices that are out there that we can use and adapt to the local context to deal with things like the thin walls in Indonesia. Where there are codes and standards, we implement them to the best extent possible. We assume that you can, rather than assume what the, using what the standard calls for concrete strength, we instead, for the design, we assume what a concrete strength that is relatively achievable, which is, again, typically around half of what the standards call for. But oftentimes, that will still work. That'll still be fine, as long as you know it, as long as you account for it in advance. Using horizontal and vertical bands, particularly around openings, has proved to be, there have been tests and studies done that shown that using bands have really, really improved the performance of the system. So, and it's relatively low in cost. We also improve the connections for the tie beams and tie columns, and also switch out the light gauge walls and improve the reinforcement at intersections. Here's an example of that. The photo on the left is typical reinforcement pre-intervention. You can see the very small hooks and the spacing of the stirrups and things like that. So on the right, what we've been doing is promoting connections with developed bars and 135-degree hooks. They're low cost improvements, but they're very valuable improvements to the performance. In terms of retrofitting, we've implemented a lot of different techniques for retrofitting, including adding tie columns and beams within existing walls, adding lintel beams. We've talked already this morning as well as yesterday about adding reinforced bands within the plaster, infilling walls, adding walls where that's feasible. That's not always feasible. One of the things that we do make sure we look into is the foundation system, and underpinning footings. A lot of times that gets kind of ignored when we're strengthening walls and strengthening buildings. We, sometimes tend to forget, oh, we need to strengthen the foundation too. Strengthening the connections, replacing the gable walls, and all of these techniques apply not just to retrofitting existing confined masonry structures, but also, as my colleague Sophia mentioned earlier, converting existing unreinforced masonry and masonry infill walls to confined masonry walls.
Hi, Tim, sorry to bother you, but we'll have to conclude in 2 minutes. Thank you.
Thank you. So retrofitting, it's a very foreign concept in some countries. And so it takes a lot of training, it takes a lot of socializing, it takes a lot of development to standardize retrofitting approaches. In some countries, they require the retrofits to meet current code requirements, which is not feasible most of the time, and is a barrier it can be a barrier to retrofitting, particularly on the cost side. So in the United States, we have guidelines for retrofitting that allows the use of specific performance criteria, that is lesser than current code, but still satisfactory for performance. And other countries have, like IE 410 in Colombia, they've implemented those to make retrofitting more affordable, more feasible, and more people more willing to do it. Using technology is important. We've developed apps, socialization apps. We've developed digital platforms for data collection. We have used AI for retrofit designs to kind of standardize the retrofit designs as well as new designs, to expedite the process and make it more accessible to homeowners, so they don't have to sit and wait for the engineer to work everything out individually for each building. So all of that technology has been used to promote confined masonry, both new construction and retrofitting. And training is very, very important, not just the builders, but also the engineers, also the government ministers, also homeowners. One of the things that we have found over the years, given that inspection and quality assurance is a huge issue, if we engage the homeowner in that process, the homeowner has the most at stake in these buildings, in their houses. So if they have the knowledge, if they have the skill, if they're empowered to oversee the construction of their own house, to make and stop builders that to enforce quality on the builders, then it's much more likely you're going to have a good end product. So also linking the payments to the quality, as opposed to just giving that the money and letting them do whatever they want with it. It does also improve shown it has proven performance, as has improving the materials. And we set up in Indonesia, where one of the many countries where masonry strength is a very common problem. So to promote that, we worked with local masons, local manufacturers of bricks in Sumatra, in West Sumatra and Aceh, to not only to develop new techniques for making bricks to make them stronger, but then promoting those bricks to the public and promoting testing of the bricks, which was not typically done before, and socializing these. And presenting to builders, presenting to homeowners how what the importance is for good quality bricks, and make them affordable so that people will be willing to buy them. And the results that we saw in Aceh from this co-op, which is still going on now, have been impressive. The compressive strengths have more than doubled in many cases. So it's been a very effective approach to deal with this very persistent problem. And I'll conclude by inviting everybody to join us in Milan for the World Conference. Professor Svetlana Brzev and I are co-convening a special session on confined masonry. Many of the speakers in these presentations, both today and yesterday, will be presenting papers at the conference, and I definitely look forward to seeing you all there. Thank you very much.
Thank you, Tim. Thank you very much. We do have 5 minutes for questions and answers, if we have any questions. I thank you, Professor Alcocer. You've already answered most of the questions in the chat. If there is anybody who would like to unmute and ask a question, please feel free to do so. There's one question in the chat. The efforts to having formal codes or guidelines for CM, as Dina has pointed out, would be bottom up. I think it's a recommendation working with civil engineering associations in the respective countries and develop uniform guidelines for CM. I think this goes back to the discussion we had in the very beginning yesterday regarding the development of codes and expanding the availability of codes into other countries. I would like to ask Tim. Sorry, please go ahead, Professor Vaibhav Singhal.
Yeah, thank you, Hassan. So very informative presentations, I think, sessions we have. So my question is for Professor Alcocer. So I'm thankful for him to share some of the informative knowledge on this retrofitting of confined masonry. And of course, there is a lot of research on retrofitting part. So a lot of work has been done on, especially on the retrofitting of confined masonry. I will say not a lot of work, but some work has been done. And major challenge, we have also done some work. The major challenge is how to anchor these retrofitting, externally applied retrofitting techniques to the base, and there are not much guidelines, because same challenge has been seen also with the unreinforced masonry. Because if there is no proper anchoring to the beam or to the base foundation, then many of these techniques are not so effective compared to. So what is your recommendation, and how these can be designed properly, and whether the guidelines which we have shown has also some recommendation on those anchoring techniques which can be used for this retrofitting measures?
Thank you very much, Professor Singhal. You touch a very significant point for the welded wire meshes to actually work properly. We started doing research on the use of nails, but separating the wire mesh from the wall, keeping the wall pretty much in the middle of the mortar layer. So in order to use some spacers, we came up with the use of bottle caps, the old-fashioned bottle caps, metal bottle caps, to separate the mesh from the actual wall. It didn't work very well because the connection became very flexible. And at some large deformations, some large drifts, the nail will come out, and then there will not be transfer of load between the wire mesh and the masonry itself. So we tested without that spacer, just attaching the wire mesh directly to the masonry wall, and it worked very well, just using common nails. And the issue with common nails is that you have to have a very proficient mason so that it really hits the nail properly. And if not, then you will sort of crack and eventually spall the piece, the unit, and then you have to replace the nail, and that takes time. So then we used powder actuated fasteners like the one that I showed. These are Hilti made, and there are other companies. And this is very good technique because you have to, of course, calibrate the amount of powder that will come into the cartridge that you use for the fastener to be installed. But the productivity is very large, and the effectiveness is very significant. So this is a very good way for fastening. Then we have also used staples like the ones that you use for barbed wire in agriculture and cattle fields and things. And that also works very well, particularly when you have soft masonry, like adobe, for example. And so we have used, and then we have also used wires. This is like a 4 or 5 millimeter diameter wire that are crossed across the wall. We place them across the wall, and we attach them to the meshes on both sides. And that also have worked very well. We even have tested some walls in which we have distributed the anchors within the wall, typically spacing at about 45 centimeters or so. And we have tested some other walls in which we only had the anchors at the perimeter. And there is no significant difference between those walls. So yes, I think it's critical to have the meshes well anchored. The better anchor that you can use is, I think, the powder actuated anchors, but they are a bit more expensive. But for rural applications, these staples that I'm mentioning or just nails are good enough. And the best is, of course, to distribute the anchors within the wall, but just having them in the perimeter of the wall in tie columns and tie beams, if they exist, that's enough. If they are properly designed for, that means that they can accommodate the design strength of the wall being strengthened by the mesh.
Okay. Thank you, Professor.
Thank you both. I think we are running out of time for the Q&A. Hopefully we'll have a bit more time after the next set of presentations as we do the panel discussion. I would now invite Svetlana to introduce the next speakers. Thank you, everyone.
Hello, good afternoon, everyone. This is our last session with the presentations, so congratulations to all of you for being around. I would like to introduce the speakers and the presentations. So the topic of this session is durability and climate adaptation of confined masonry construction. The first topic is durability of confined masonry construction, and the speaker is Sebastian Kaminski. He is associate structural engineer working with Arup in London, and he's working in specialist technology analytical research team for over a decade. He has worked on structural and seismic engineering projects of humanitarian and developing world contexts across Latin America, Africa, and Asia. His focus is on appropriate, sustainable, resilient, and affordable schools and housing in seismic areas. So I would like to invite Sebastian to share his screen and start the presentation and keep on time if possible. Thank you.
Thank you very much, Svetlana, for the introduction. And thank you, Dina and Asana and everyone for organizing this excellent event. I'm going to try sharing now. Hopefully you can see this. Can everyone see that?
Yes.
Excellent. Great. So I'm going to talk briefly about durability of confined masonry. So I'm going to start off by talking about design life. So what is design life? So design life is generally defined as the minimum period within which the building can be expected to perform for its purpose without major repair being necessary, with minimum maintenance. So that's very important when we understand what is design life. We're not talking about significant maintenance. We're not talking about significant repair. Now, most international structural design codes actually implicitly, without specifically stating, sometimes they do, sometimes they don't, but often they're intended for buildings to have a design life of 50 to 60 years. So reinforced concrete, steel, masonry, and timber codes pretty much all say 50 to 60 years internationally, but sometimes it's not explicitly stated. So that's the status quo for most systems around the world. Now, when we talk about confined masonry, it's often proposed for low-income communities, and they don't have significant resources to repair buildings. So how can they afford to repair damaged buildings? Equally important, there's actually no simple solutions for concrete repair once concrete is carbonated to the depth of steel. So the concrete cover that we have that protects the steel reinforcement provides that protection against carbonation, against corrosion. But there's a process, and once that carbonation layer has actually met the steel, there's nothing really one can do to reduce corrosion. Efforts like painting and render help a little bit, but they're not that reliable. So really what we need to do is have a much more reliable method of providing durability. And that's what people use in reinforced concrete design. And it's important to also consider that corrosion is a major contributor to building collapses and earthquakes. We saw a lot of that in the Musni, Ecuador earthquake 2016. Therefore, we would strongly recommend designing confined masonry for a reliable design life of 50 years to meet what other codes are saying for other permanent buildings around the world. And considering that most codes for affordable housing also recommend a design life of 50 years using other materials, why should confined masonry have a reduced design life? So that's our proposal in terms of meeting the status quo. Now, what governs design life in confined masonry? Firstly, the ambient conditions. How aggressive is the environment? So that's humidity, rainfall, temperature, and how close it is to the sea. And that's where we get salt, which can accelerate corrosion. Other variables include concrete strength, the cover to reinforcement, the weathering resistance of the masonry, and the strength of mortar. So lots of things to consider. We can break exposure conditions down into roughly three different areas, and very few areas fall outside of these three categories. Normal conditions, and this is in a moderate to high humidity zone, but not coastal or mountains. Coastal conditions, which are typically within 1 to 2 kilometers of the coast, so not common, but those conditions are far more aggressive. And finally, mountains, and that's buildings which experience temperatures below 0 degrees over their life, and they're exposed to additional freeze-thaw weathering. Now, if we look at what other codes say about durability, we should look towards ACI 318 quickly, because this has actually influenced a lot of codes around the world, and it's also influenced some confined masonry codes around the world. And it's been acknowledged by various ACI committees that it's actually significantly less conservative than European practice, and basically unconservative in compared with international state of the art. Minimum strengths are, for example, half of European practice and covers around 3/4. ACI 318 is designed for US buildings, which are typically sealed and air conditioned. And also bear in mind that the minimum strength in ACI 318 are rarely used in practice, as ready mix comes in stronger strength. So the issue that if we're going to copy 318 for confined masonry, which has happened, is that it doesn't really apply, but it has influenced other codes significantly. Now, let's take one national confined masonry code around the world. I'm not going to mention which one, but just as a case study, the minimum concrete strength specified is actually 17 MPa. Minimum cover to reinforcement links is only 15 mil if plastered, 25 mil unplastered. There's no consideration of coastal or mountainous conditions. We've done our own independent assessment and compared that against international best practice, and that suggests that the service life of buildings built to that code would be less than 10 years in normal conditions, or even less than 5 years in coastal conditions, which I'm sure you'd agree isn't what we're looking for. Maybe 50 years is too much, but less than 10 or 5 years isn't really what communities want for permanent housing, or what they expect to be permanent housing. And this assessment is supported by visual observations internationally. So we think this is just a bit of a gap in the code, and unfortunately it's been influenced by ACI 318. And so what we've tried to do is look at European practice, which follows a bit more state of the art. And this is based on European practice. And these are some recommendations which we'd like to give. These are preliminary recommendations. If we want to achieve 50 years, which may be very difficult, but if we want to, this is the sort of minimum strength and a cover that we would need to achieve. Whether achievable or not is another question, but this is just what we need to reliably achieve a 50-year design life. What you can see is generally we're talking about a 28 MPa concrete strength, which is hard but not impossible to achieve with a site mix concrete, and probably 4 MPa minimum mortar strength. And concrete covers significantly greater than what we might typically use for confined masonry. But we can reduce those if we have additional render. That helps significantly. So for example, externally exposed confined masonry elements without render would probably need 50 mil of cover for a normal environment without render. But if we add 30 mil of render, we can start to achieve 35 mil of cover, which is a lot better. And internally, it's a little bit better because we're slightly exposed. These are for non-air conditioned buildings, which is quite typical for confined masonry buildings. Now, if we talk about coastal conditions, which if we remember are within 1 to 2 kilometers of the sea, so that doesn't apply for most confined masonry buildings, only probably a small subset, but these conditions are much more aggressive. And immediately we need something like 60 mil cover internally and externally because of the salts in the air, but also the concrete strength needs to be around 35 MPa, which is probably not achievable with a hand mix. And that begs the question, is confined masonry appropriate in coastal conditions in areas which are close to between 1 to 2 kilometers from the sea? You also start to need stainless steel, and that special stainless steel for bed joint reinforcement. You can also achieve it potentially with heavy galvanized steel, but that's not just normal galvanized, that's a special galvanized steel, and that still requires render. And for mountainous conditions, they're similar to normal conditions, but maybe a slightly higher concrete and bed joint reinforcement strength to stop freeze thaw weathering. Other considerations for durability. So most codes are quite consistent in this, that the minimum characteristic strength of fired clay bricks should be in the region of 4 to 5 MPa. Minimum characteristic strength of bed joint mortar, probably around 4 to 5 MPa as well. And in mountainous climates, bricks should have adequate freeze thaw weathering as well. How can we reduce those requirements? They are quite onerous. How could we further reduce them? Well, we could further increase the concrete strength, which is difficult to achieve and quite expensive, and probably not achievable with site mixed concrete. We could try and achieve greater control over the water cement ratio. Again, very difficult to achieve with the site mixed concrete. If we do use alternative cement types, that can help a little bit, like certain pozzolanic cements are better than conventional Portland cements. And also, I should also mention, if we're in a very dry environment, like a desert environment, that also permits lower covers, but most confined masonry buildings aren't really in that sort of environment. So next steps. So these are very onerous requirements. We fully appreciate that, but this is following the state of the art. This is what we would need to achieve 50 years. So how can we reconcile these needs and requirements with the current requirements? Maybe we can't achieve 50 years, but at least maybe we can improve the status quo and provide a minimum standard for durability internationally, because we certainly don't want buildings lasting 5 to 10 years. Now, very quickly, I've been asked to talk a little bit about climate adaptation for confined masonry buildings. I'm going to talk about new buildings. So obviously with climate change, we need to reduce our embodied carbon. So how does climate change influence confined masonry? Probably in simplistically, new buildings in 2 different areas. Firstly, confined masonry uses carbon-intensive materials, concrete, steel reinforcement, fired clay bricks. Firstly, climate change may change design requirements. If we focus on the first one, we know that concrete, steel, and fired clay bricks are all carbon-intensive. So how do we reduce that embodied carbon? Firstly, designing efficiently, and that's where the codes come in. If we design the codes, that certainly helps, and making the codes safe but efficient also helps. Also, designing for 50-year design life, not only does it help the communities, but it will reduce the embodied carbon of buildings, because a reduced design life is actually less sustainable because the building has to be demolished and then rebuilt more frequently. We can maximize the use of lower carbon concrete, more GGBS and pot ceramic cement. And potentially, could we consider compressed soil stabilized earth bricks for the wall infill? Just a thought to reduce embodied carbon. And secondly, in terms of changing design requirements, so changing weather patterns may result in stronger storms and higher humidity, and that gives the potential for higher wind loads and increased risks of corrosion. Something to consider, and those are reasons why it's even more important to follow code requirements and also try and achieve minimum durability requirements as well. Thank you very much. Hope that was of interest.
Thank you very much, Sebastian, for being on time and for a very interesting presentation. Does anybody has any questions? I believe there is one question on the strengths. Maybe if you can take a look. I'm not sure if it is for you, but if not, we can try to answer as well. But if you have any question regarding the I don't think the questions are necessarily for you, but we will answer as needed. Any specific questions for Sebastian related to durability of masonry? We can have of confined masonry. We may have a couple of minutes. If not, we will thank Sebastian for a very interesting presentation and proceed with the next presentation. The next presentation is on retrofitting of informal housing for climate adaptation, and the speaker is Anna Pavan. Anna is engineering program associate with Build Change, structural engineer specialized in seismic design of buildings. She started her career at Open Partners for dedicated 10 years to working both London and Madrid offices. And she has been experienced in design, construction management of buildings in different countries. And for the last 7 years, she has been working for Build Change, primarily focusing Latin America and Caribbean. So Anna, please proceed and please go ahead. I see you have shared your screen already. Thank you.
Who's going to introduce the reactor?
Thank you very much. Hi, everyone. I hope you can see my screen. Can you please confirm?
Yes.
Correctly?
Yes.
Perfect. Thank you very much for the invitation. It's an honor for me to be here today and present to you some of the results of the work we've been doing at Build Change. I'm going to talk about retrofit of informal housing for climate adaptation and mitigation. Let's start from here. Everybody should have access to a resilient home that can address the basic needs, protect families from hazard, climate extremes, and be a safe place for growth and opportunity of the family. Well, the reality is that most and the majority of people nowadays in the world do not have this basic right assured. Accordingly to UN Habitat, by 2030, about 40% of the population, of the world population, will be living in unsafe and substandard housing. Urbanization has increased exponentially over the past century and continue to rise. In many cases, governments have struggled to meet housing demand, or the formal housing market has been inaccessible or unsuitable to newcomers, leading to an increase in informal housing. Informal housing are houses or building in general, building that has been built without the input of qualified designers, as an engineer, architect, or technician in general. And in most of cases, they are very vulnerable from a structural point of view, but also they lack some basic habitability requirements like access to potable water, have correct sanitation, installation, or access to electricity. All these factors together is what we call qualitative deficit. These homes are generally and very vulnerable to all sorts of natural hazards like earthquake, windstorms. I put there some data from the last few decades of the most impactful, if you want, events. But also we need to consider that they are generally occupied by lower income lower income part of the society. As people keep on moving, the global population keep growing and more people keep on moving in urban areas, the competition for lands intensified and the exposure to risk of this type of building increase. As a result, the qualitative housing deficit is increasing exponentially, and this is taking place backdrop by a continued rising of threat and new natural hazard. Climate change is just worsening this situation because more floodings are more frequent and more severe. Hurricanes are more frequent and stronger every year. So the global risk is increasing. But masonry buildings or this kind of informal construction or earthquakes in general do not have to be deadly or generate losses and to be at such a level of disaster. A build change we advocate to that improvement of existing houses where people already live in, as a valuable way to reduce risk, whenever this is, of course, applicable and doable in the general surrounding. The majority of homes can be made safer using relatively simple, tried and tested solutions that already exist. One of the most common retrofit techniques, I'm not the first one to present about this, is to convert unreinforced or partially confined or partially reinforced existing masonry houses to confined system. This generally means to introduce tie columns, tie beams, lintel to complete the system. Masonry construction in lower income countries and also in informal construction represent between 50 to 90% in some realities of the existing global stock. So finding solution and the conversion to confined masonry system is something that very typically is implemented. I'm showing here just very quickly two examples, one from Guatemala, the other one from the Philippines, a project we've been working in. By converting existing unreinforced system to confined system, we make a house safer. A safer house can be referred to houses that being either built or being retrofit to withstand natural hazards. So they have a reduced vulnerability and they protect the people that live in. Safety thresholds are different in different countries. Of course, they're set by the local building codes, but in general, let's say they have as a minimum level of goal or objective the life safety or collapse prevention of the people that live in these houses. Of course, we can build new building and new houses to be resilient and safe from the beginning, but also we can retrofit existing house to be safe. However, since few years already at Build Change, but I think the global engineering community, we've been focusing or translating from the concept of safer housing to a concept of resilient housing. A resilient house fulfills and exceeds the aspect of a safer housing. In fact, it is a house that provides safety to the occupants, but also is a locally appropriate, is a healthy and secure space to be occupied. It is affordable and it is a secure financial investment for the people that live in, meaning they're not banned or expected to lose their property every time there is an event affecting the area. Moreover, resilient housing initiatives are sustainable in the local reality and they are scalable. When the problem is touching 50 or 90% of the existing building stock, we need to think about scalability. Resilient housing beyond safer housing has all series of benefit. Team, Sophia, many of my colleagues already talk about it. It leads to a higher homeowner satisfactions. It reduces the needs of occupying new land. It reduces also the needs of bringing new infrastructure like connection to main services in the new lands that generally new construction involve. But also, I would like to briefly show you the impact on costing and the financial benefits that retrofitting existing rather than building new has. What I'm going to briefly show you here are the results that are included in a more detailed study that is free for download in our website, that is titled The Cost of Improved Vulnerable Housing. It is a study that we elaborated after based on over 1,400 retrofit projects around the world that we've been working on. And the key finding was that retrofitting and improving existing housing on average around the world costs 23% of building the same housing new in the same location. So 1/4 on average. Out of this 23%, around 60%, 60% of this cost goes in structural improvement needs, as I say, like conversion to confined masonry systems, for example. The other 40% of this cost is generally dedicated to habitability upgrades, finishing, painting, for example, or some repair and touch up of damages that were already there, cracks in the wall, some reinforced concrete repair. And this kind of investment generally meet the homeowner expectation, because an improvement of habitability upgrades and the finish is something they can clearly touch and see immediately. So this is why we're leading to a higher satisfaction immediately. Another key finding about cost that I would like to show you here is that the study revealed that retrofitting for multi-hazard, yesterday we were talking about this, is not necessarily more expensive than retrofitting for one only hazard. Our study based on earthquake and wind combined together in locations like Haiti, the Philippines, and compared to new construction, the benefit is still quite significant. The cost is around 25% compared to new construction. So multi-hazard, retrofitting for multi-hazard is also something that we should bear in mind and consider when we develop program and strategies. It is also a safe and convenient, financially convenient way to support the urban density, which is a phenomenon that is happening. Retrofitting a house to safely withstand a vertical expansion, we found that is cost on average 35% of building new. And last but not least, we found that retrofitting before a disaster is significantly more convenient than retrofitting that after a disaster. As simple as that. We have less damage, we have less materials to be implementing, we have less money that needs to be invested. Another fundamental benefit that retrofitting new house has compared to building new is a reduction on the embodied carbon emission. We recently published a new study that is called Saving Embodied Carbon Through Strengthening Existing Houses. Again, it is free for download from our website, and it is a study that actually proves how much retrofitting rather than building new can actually reduce the impact of the construction we make. It is a real world result, meaning that this study has been based on projects in 6 countries around the 4 continents we are currently working on. These are real projects. These are not theoretical or modeling results. So this is based on what we actually built. Let's start with the first key finding that I would like to show you. So improving housing rather than building new save about 2/3 of the emissions, CO2 emissions in the environment, meaning that for each new house that we build, we could have retrofitted 3, having the same impact. In absolute terms, I like the picture on the right because it gives you the dimension of what I'm talking about. So we could save for each house retrofitting about 18 metric tons of carbon emission. This is equivalent to 18 flights between London and New York. It is equivalent to 1,000 steaks and beef not served. It is equivalent to 4 people not driving a car for a whole year. So if you put it under this scale and this order of magnitude, you can understand the potential benefit that retrofit has rather than building new. This is a very important data if we consider that buildings and construction in general, they cause 40% of the emissions, the total global emission that we currently have in the world. And out of this 40%, houses represent 17% of the emissions. So we must reduce both the embodied carbon and the operational carbon related to houses. For years, the attention has been in reducing the operational carbon. By the way, I just opened a parenthesis on the definition. For operational carbon, we refer to the emission associated to the energy used to operate the building, meaning related to heating, the electricity use, or the power of appliances. Embodied carbon is instead referred to the emission associated with the materials and the construction process over the whole life circles of the building. A lot of attention has been put in the years over on the reduction of operational carbon. So we have improved the efficiencies of our appliances in the house. We have improved the efficiencies of our facades, the roof, reducing the need for energy to operate the building. But the embodied carbon is still too high, yeah? So we need to work to reduce embodied carbon, which is, as I say, carbon related to the production of materials and the construction. Here, I just briefly show you the life cycle of a building. And embodied carbon is present throughout the life cycle, but in the first two phases, which is the product and the construction phases, where between 70 and 95% of the embodied carbon is actually being produced. So that is the phase Sebastian just talked about, like materials. That is the phase where we need to focus our attention to actually effectively reduce the emissions. Once the building has been built, it doesn't really matter, to be honest. So it is very, very relative, the fact that if it has been retrofitted or built new, already resilient. The operational carbon and the embodied carbon, once the building is being built, is very similar in the two cases. So new construction versus retrofit really has a huge difference in the first two phases. This is a schematic representation of what comes from the Design for Zero study published from the ISRAC-T. Substantially, the most effective way to reduce the carbon emission is, first of all, build nothing, which is not sustainable. We've seen that there is demand for new houses and demand for construction and of improvement of existing houses. So it's not that we cannot build anything. But the most efficient way to reduce the emission is actually to build less. And of course, retrofitting is a way to build less. Other key finding that we find through this study is that retrofitting for vertical expansion also of the house is still convenient in terms of reduction of carbon emission. You see there that the savings are still around 47%. And most of the emissions are generated by the use of cement and steel and masonry units, but mostly 60% comes from cement and steel. So confined masonry under this perspective is a good way to go, in the sense that you use tie beams, tie columns are smaller elements than RC frames, for example, moment resisting frames. So it is, confined masonry is also a good way or a good system to use if we bear in mind reduction of emissions. So retrofitting existing house is an effective strategy for climate change mitigation, but also is an effective strategy for climate change adaptation. And to explain better about this, I would like to take you with me to Honduras, in particular to the Sula Valley, which is a very florid agricultural valley in the northeast of the country, facing the Caribbean side. It is crossed by
Excuse
two.
me, Anna, can you please, sorry for interrupting you, but can you please try to wrap up soon? I'm sure
Yes,
it's
yes.
your overtime. Thank you.
The Sula Valley is subjected to floods, very frequent floods since ever. However, climate change and the most frequent rains and hurricane season worsen the situation. So we have more recurrent floods every year with higher water levels. This is a picture taken in 2020 when Hurricane Eta and Iota affected the Sula Valley with water levels up to 3 meters. In there, we started implementing a climate adaptation project together with the Honduran Red Cross and the National University of Honduras, based on the fact that the people, when they are subjected to floods, do not want to leave their house. You see that they camp in the roof of their houses, they camp in the banks of the canals that are in the area because they don't want to go far away. They don't want to leave the house unattended for a long time. So our project substantially focused on taking existing single-story houses and retrofit them and vertically expanding, generating a safe second story where people can find refuge during these events. They can stay close to their house at least for a few days till the helps will come. The second story unit is also energetically independent. We install solar panels, rainwater harvesting, biodigester to make sure that people have potable water and solar power energy during the emergency. So we had a proof of concept at the end of 2022 where the tropical storm Julia affected the area. We were building some of the houses, some were completed, and you can actually see how people store all their belongings and also the belongings of the schools and the neighbors in the second story. So this is a way to help people to stay there, not to leave their country, to reduce forced migration, and especially from areas that are so significant for a country like the Sula Valley, that represent 50% or produce the 50% of the national income of Honduras with its agriculture and its infrastructure. Here are some very small numbers about the impact and the reduction of CO2 emission. Each house in Honduras allowed to save 9.5 tons, metric tons of carbon emission compared to new construction. So
sorry, Anna, we need to ask you to wrap up, please.
Thank you very much. I finished.
Thank you very much, Anna. And due to the fact that we're running late, we don't have time for question and answer related to your presentation. But if any of the colleagues have a question, please ask in the chat, in the question and answer box, and then Anna will answer, I'm sure. And we'll have a 5-minute coffee break, e-coffee break, and then we'll continue with the next session, which is reactions, followed by the panel. Thank you. So 5 minutes, I think it's a good break as announced earlier. Thank you. See you in 5 minutes.
Thank you to all the speakers, and we will indeed look into some of the questions that I've raised up in the next session anyway. So thank you again and enjoy your break. Thank you. My camera doesn't start. Okay. Welcome back, everybody. I hope that you had time to at least reach some refreshment, if not consumed it, and you have it next to your post station. We are now starting the last but not least session of this symposium together with the further discussion. So we have heard from the speakers of various experience across the world, and we now have 6 reactors that are independent from some of the country which we have heard experience, and they will tell us what do they think of what we have been hearing so far. I need to remind you that each of you only has 5 minutes. So I will ask you to be very brief, and to the point, and whatever you want to raise and ask to the speakers, please do so, or indeed tell us about your experience. We also have a contributor from Iran, Professor Mahdi Iqbali. He was not able to join us yesterday in the session of experience from Iran. So you will also have an opportunity of using 5 minutes to tell us more about what's happening in Iran after the reactor. So the reactors are, and I'm not going to introduce you formally, Julian Tambu, Heman Koshik, Kaiser Ali, Ramesh Guragain, Unita Idris, and Dexter Lowe. And I will call you in this order. So please, Julian, the time is yours for 5 minutes.
Okay, can you see my slides?
Yes.
Yeah, okay, so I'll be very quick. So now, first of all, I have heard all of you that speak on confined masonry applied to many other countries, mostly seismically active countries. So I come from Sri Lanka. So just wanted to say something about Sri Lanka, the background. Yeah, Sri Lanka, as some of you may know, we are in the Indian Ocean. We have floods, landslide, and cyclone, and also interplate earthquake. Although some portion of our country can be considered as moderate seismic regions, and we had tsunami in 2004. I will talk about that in next slide. But since it is an island nation, recently Global Climate Risk Agency has rated Sri Lanka as the second most vulnerable country for climate-related disasters after Peru. So in 2004, we had this, we were subjected to this Indian Ocean tsunami, which has caused around more than 35,000 deaths after Indonesia and cost about 2.2 billion worth of losses. Okay, but I think this tsunami disaster was a turning point in Sri Lanka, because till then we didn't have any disaster preparedness management policy or act in the government. So actually, the 2004 tsunami actually led to a development of Disaster Management Act, which was passed in the Parliament in 2005. Because of that, we have established a National Council for Disaster Management, and we have now Disaster Management Center, which overviews all the disaster-related responses, not only tsunami, in general now, if it is a landslide, flooding, and cyclone warning, all those things. So, 2004 tsunami, although it was a devastating event, it actually has created some more awareness for disaster preparation and disaster mitigation measures in Sri Lanka. So, which actually led for developing these kind of guidelines in Sri Lanka after 2004 tsunami. The people have more understanding and more concern on disasters. Like we had, till then we didn't have any much preparation for detailing on buildings and like that, for specifically for earthquakes. But because of the tsunami, it has led to this kind of documents. So it's particularly URM, since till then we were mainly for encouraging people just building URM buildings. But then these manuals actually have indirectly asked people to go from URM to confined. So ask them to add tie column, tie beam. So it kind of, it was not mentioned explicitly as a confined masonry, but if you look at the detailing, actually what they are saying, this document are saying confined masonry. So up to this, it's about Sri Lankan perspective, but as a masonry, work on masonry structures, I have listened to you yesterday and today earlier sessions. Yes, I would echo again, yeah, we have to have a more detailed design provisions in confined masonry already there. I think some of those who have worked on these manuals, guidelines are already in the forum today and yesterday also. So, but overall we have to go forward, and some of the gaps we have discussed, but it has to be improved, and we have to go forward. Especially, we can do research, but finally the cycle completes, but when it is only design provisions are developed. So then actually we, as a research group, we mainly worked on reinforced masonry, but confined masonry is another alternative. Reinforced masonry, another alternative for unreinforced URM, but confined is, but recently—
You have less than a minute.
Yeah. There recently, these nominally reinforced systems in masonry have been questioned by, well-established reinforced concrete or steel groups, how you can assume it can work. We all know it can work well, but how much it can work well, I think we have to all work together to show that it has more, it has improved performance, but little bit more. And Sri Lanka, yeah, since I said it's climatically sensitive country, I just show you Sri Lanka is more sensitive to climate-related disaster. All the schools were affected by rain, flooding, and landslide. Even air pollution. So, and the corrosion, Sebastian talked about corrosion, but most of the coastal schools and the mountainous region schools, we have database of corroded schools, and we are monitoring them. That's all. So maybe we can discuss this later, and that's it for me. Yes.
Thank you very much, Julian. And quickly and swiftly, please, Herman Koshik.
Thank you, Tina.
Thank you, Herman.
Yeah, as a reactor, my role is to give a reaction. And obviously, I have just one reaction, and that is wow. This was such a fantastic, such a wonderful event. Thank you so much, Dina, and your team. This wonderful event. And really, there are so many topics, so many interesting topics, starting from analysis, design, retrofitting, school buildings, then codal developments throughout the world. And also we learned about the practices in different countries, especially the presentations were made on countries like Indonesia, Kyrgyzstan, Iran, Peru, Mexico, along with some, of course, some studies on India and Colombia and other places. There were some very interesting discussions and observations on the comparison of masonry infill reinforced concrete buildings with the confined masonry buildings. And that is where my worry is. So when we are doing a lot of research, a lot of work has been done, codal developments and everything on confined masonry. My question is, are we moving towards masonry infills? Are we trying to design these tie columns and tie beams similar to the columns and beams in the confined masonry buildings? So if the objective is that, then I think we are going in a wrong direction. So there is a reason why tie columns are different than the reinforced concrete columns and the tie beams are different than the reinforced concrete beams. And we must respect that and continue our quest towards finding out new ways on how to improve the capacity, performance of these confined masonry buildings, rather than again trying to make them just like masonry infilled RC frame buildings. So I completely agree to what Professor Alcocer was mentioning yesterday and even today, that in future, will there be a difference between masonry infilled frames and confined masonry buildings? So that is one important issue, and particularly because we are doing a lot of work now, and I'm really glad to see that This is the group across the world these are the people who are working on confined masonry buildings. So we are under one roof. I don't think there is any such group existing for reinforced concrete buildings or for steel buildings or for any other building. So I think the confined masonry network that started some time back, it has expanded so much globally now that yesterday I think there were around 150 participants in this symposium. So congratulations to all the organizers. Thank you for inviting me here. I just have one more point to say that it is clear from the wonderful presentations yesterday and today, there are so many challenges, particularly the masonry. There's so many things to do. And we have to look for opportunities for funding in different places so that these challenges can be met, so that we can find out ways to develop new methods for analysis and design of confined masonry buildings. And obviously, we have learned from so many learned participants and the presenters the beautiful aspects of confined masonry building. So once again, I thank you, Dina, and your team, Svetlana, and for giving me this opportunity to speak here. Thank you so much.
Thank you very much, Hemant. Thank you for keeping it to time. I think your call for joint efforts is very important, and I'm sure that we will discuss way forward in the panel after this reaction. Thank you. And now to Kaiser Ali, please. Kaiser, are you online? I can see. Yes, you are. Okay, that's
Thank
great.
you.
Thank you.
I will
Please.
share my screen. Please
yes.
confirm.
Yes, we can see your screen.
Okay. First of all, I would like to thank the organizers for inviting. I am Amir Raza from University of Engineering and Technology, Peshawar. I am here to present on behalf of Professor Dr. Kaisar Ali, who is Meritorious Professor and Vice Chancellor at the University of Engineering and Technology, Peshawar. I will discuss the following research on confined masonry in Pakistan, construction manual developed in Pakistan, the building code of Pakistan.
Your
and
slides are not progressing. We just see the first slide. So either you put it in show mode, or yes, you can go. You can progress
Okay.
like this. But remember that you only have 5 minutes, and I see that you have a lot of slides. So you need to be ultra quick. Otherwise, I will
Yes.
have to cut you.
No, I will quickly go on them. Thank you. Okay, on October 8th, 2005, Pakistan experienced its most devastating earthquake on record, registering 7.6 on Richter scale, hitting Kashmir and northern regions. Official figures indicate that more than 80,000 lives were lost, with 1,000 injured and million displaced from their homes. Prior to the 2005 earthquake, confined masonry was not a commonly used construction method, and there were no established design guidelines and construction standards available in the country. Following the earthquake, effort commenced with experimental and numerical investigation into various building systems aimed at constructing safer structures. Confined masonry was also one of them, which emerged as one of the systems explored for its potential and seismic resilience. The Earthquake Engineering Center at the University of Engineering and Technology, Peshawar, established in 2005 after the earthquake, played a crucial role in experimental testing of seismic resilient building system, including confined masonry. Here is a list of few studies that were performed at the Earthquake Engineering Center. This is one of the video of experimental testing I would like to share. In this video, confined masonry structure and unconfined masonry are compared. So the left side, this was a confined masonry building, and it performed very well against the unconfined masonry. In the response to the urgent need for practical guidance following the 2005 earthquake, the Earthquake Engineering Center developed a field practicing manual, which was published in both English and Urdu languages to facilitate the local workers. This manual, featuring illustration of both reinforced concrete frame and masonry, confined masonry, provided step-by-step instructions and construction details. Some of the pictures from the manual is presented on this slide. It was distributed extensively during the training session for engineers and contractors. A specialized manual designed for constructing confined masonry building in earthquake-prone area of the country was also developed, and this manual is also available on the website of Confined Masonry Network. The manual offers guidance on material and visual aids for constructing earthquake-resistant confined masonry buildings. A specialized guide titled Seismic Retrofitting and Repair Manual for Building was also developed under a project of Earthquake Risk Reduction and Recovery Preparedness Program, which was sponsored by the UNDP in 2009. This manual served as a comprehensive resource for retrofitting masonry building. In 2007, a significant milestone was reached with incorporation of a section on masonry, which specifically covered confined masonry as well within the Building Code of Pakistan 2007. The Building Code of Pakistan provides guidelines for ensuring structural integrity and seismic resilience of buildings. The code addresses key components such as band beam, columns, and walls, offering precise guidelines to enhance the earthquake resistance of structures. These recommendations include specification for placement and reinforcement of horizontal and vertical elements. Since 2005, there has been a notable rise in the adoption of confined masonry in Pakistan. For example, between the year 2015 and 2020, over 1,200 schools have been constructed in the country utilizing confined masonry technique under the Hamkadam School Construction and Rehabilitation Program alone. And the figure are increasing day by day. Thank you very much.
Thank you very much. Sorry, I didn't catch your name, but thank you on behalf of
Amer Raza.
Amer Raza. Thank you very much, Amer. And in fact, it was great to see the school of the 2015-2020 program on which we worked very closely with Kazar Ali. So thank you.
Yeah.
And I hope that we see you in Milan to discuss more the activities in Pakistan. Thank you again.
Yes,
And
okay.
now
Thank you.
to Ramesh Guragain, please.
Yeah, thank you very much, Tina. I'll share our experience from Nepal. We are new in confined masonry. We don't have the tradition of constructing confined masonry, but at the same time, in terms of the building typology, we have less than 3-story buildings of about more than 90%. So, it's already low-rise buildings in most part of the country, including the semi-urban, peri-urban area. We have reinforced concrete buildings with masonry infill. So all the ingredients required for the confined masonries are already there. It's mostly, for the residential buildings, the construction mechanism and system is more of the owner-controlled, a bit informal setup of the construction. And still the construction quality in terms of the concrete quality is not good. Still, people thrive for the reinforced concrete for the social status in comparison to the masonry or reinforced masonry. So given all these conditions, the scope of the confined masonry is very high in Nepal. So realizing this, we started a confined masonry initiative, combining several institutions from Institute of Engineering, Department of Urban Development, Building Constructions, Build Change at that time in Nepal, NSET, and other organizations. And then we, considering with some objectives that, realizing the importance of the confined masonry and also looking to the potential there, for 4 or 5 objectives that, we may our code already recognize confined masonry in terms of the design parameters. We don't have the proper guideline adopted for Nepal. Has very insufficient or inappropriate level of the awareness at the different levels, starting from the designers to the policymakers to the implementers and then building owners. So realizing all these potential the gap, we started this initiative, and then we prepared some calculations for different types of the calculations using Nepal code for the simplified method, straight type method, white column method, other methods, and then try to adopt the the code or the standards from the confined masonry initiative and ERI in our case in Nepal. But still, that initiative, the number of the meetings reduced, and then still we could not complete all the the whatever we desired. But I think listening to all the presentations today from these speakers, I think it's still, and then also having experience on retrofitting of many masonry buildings and also the RC buildings with masonry infill, I think we can adopt the confined masonry for the new buildings as well as for the retrofitting in Nepal, and there is a high potential for that. Some of the questions, some of the friends from Nepal already raised, that's valid also, that we thought even in the confined masonry initiative in Nepal that how they perform for the stone masonry as infill for the confined masonry. I think it's a matter of the research that may be important for Nepal, for especially for the mountain areas, and also as Hemant mentioned, because we have mostly the the masonry infill reinforced concrete buildings. So changing those to the confined masonry principles and retrofitting those, we may need to explore further in terms of the implications and then the effectiveness. So if any of these speakers have those ideas, you may share. So that's all. Thank you so much, and congratulations. It was very nice discussions. Thank you.
Thank you very much, Ramesh. Yes, maybe something that we will pick up later in the general discussion. But to me, we always need to think of what are the vernacular type of constructions, and in many mountainous area of Nepal, you already have timber frame coupled with stonework and so on, and some of them actually work very well, some of the vernacular architectural type. So the principle then is not very different, because the timber behave like the ties that the concrete are for the brickwork. So how to render that type of construction modern and make it more feasible, and it's also probably more sustainable than bringing concrete to the mountains. So let's see how we can improve on that. Okay, next one, Unita, you were on, and yes, please, Unita Idris from TMRC. Thank you.
Thank you, Dina. We heard so much about the confined masonry for these 2 days, and we already heard about the performance of the confined masonry structures from Dr. Lim, and also from today from Tim. Yes, I do agree about the about the explanation, and I quite interesting about the presentation. Indonesia indeed has an earthquake standard for building, which is including SNI 1726 and 2019, but it's for building for the load earthquake load. And in 2020, there was the public guideline for schools for the standards and the damage assessment of the school and madrasah, in which include in SEDG CK number 47 in 2020. And this guideline not specifically mention about the type of the construction. This guideline have the uniform design of the schools based on the occupation number and number of the story, and it is referred to the concrete reinforced concrete, not specifically about the confined masonry, even for the one-story building structures. And Indonesia has reinforced concrete standard, which is SNI 2847 2019, refer to ACI 318M 14. But yes, confined masonry has no standard yet. But we do have the guideline as mentioned previously. And confined masonry is the majority type of the construction that could be found in the school buildings, in the area of especially in the sub-district area. And this type of the structures, yeah, we can call it the confined masonry, and has and also have less of maintaining. And in the recent case, which is the earthquake in Cianjur, West Java, we found that most of these type of the construction have the moderate to severely damaged. Yes, the confined masonry structure of the school. And this could be caused, we conclude that this could be cause of the, we can call it under reinforced, I mean the less size of the tie column and the tie beam, and some of the absence of the tie beams. But it unfortunately it is for the, we can say it for the house or residential building, which is we call it as an engineer, non-engineer building, or in previous presentation we call it as an informal building. But school supposedly to be the, I mean, the engineer building, which is designed and also have the standard. But yes, we found that the absence of the tie beam, especially in the gable of the roof gable, because mostly our type of the roof is the kind of the gable roof, and the minimum cover of the column, the tie column. And I could also see the minimum cover that could cause the corrosion, as I mentioned previously in Sebastian presentation, that I could found it in Aceh school, I mean, one of the Aceh, and also in Palu school, Palu building school. So because we are in the coastal area, that like this require of the cover thickness, it's really important to, you know, yes, to increase the durability of the buildings. So I do agree about the, I mean, the society, I mean, spreading the guidelines to the local builder, especially in the sub-district area, and also enforcement about the guideline. Or if we already have the standard, yes, we need the code or the standard, and then having the enforcement of the standard. And thank you for the symposium. That's quite interesting.
Thank you very much, Unita. Thank you. And swiftly, we'll go on to Dexter. Thank you, Unita, for answering some of the presentations points. Dexter, please.
Yes, I think everything has been said, and I will be very quick, Professor Dina. Just 3 points. Number one, thank you for this excellent webinar, from basic concept to cutting edge research, and more importantly, to actual application, especially for us in the Philippines, where we can resonate the need to make our houses, our schools more resilient to many types of hazards. In the Philippines, the confined masonry is not as popular as the reinforced concrete, whether that you are in the university or you are in the construction industry. It is not as diverse, as in-depthly discussed. And so that is why, even if there is a chapter in our structural code on masonry, but I think the challenge here is we need, for example, I learned yesterday, like you need to do finite element, while when the application is more on the lower economy. For example, if that is the case, I mean, that's the case in the Philippines. So there is some disconnect there, which could pose a challenge. But when I dive deep in this 2-day and night here in the Philippines, it has kept me alive because there's a eureka moment for me here, Professor Dina and Asana, and I'm so grateful because I've surveyed a lot of buildings in the provinces. And we are always pushing, assessing these buildings as reinforced concrete, where I learned now that perhaps the better hope for these houses and units to be retrofitted, as Anna was saying, from under confined to a confined setting, could probably the strategy would be to make them in a category of confined masonry than to push it into a reinforced concrete where they actually fail in terms of assessment and things like that. So this is my eureka moment, not only for learning, but to give hope to these people who are really challenged during climate and during earthquake hazards. Thank you very much.
Thank you very much, Dexter. And if that's one of the outcome of the symposium, that's actually very good. And it's politically and socially very important that we also classifies the local building for what they are, as you are saying. So if Madi, Bali, are you ready? You have 5 minutes to give us some feedback from Iran.
Hello, do you hear my sound?
Yes, we can.
Yes, first of all, I have to say that thank you for this effort. It was really interesting. Actually, what an effort this is. This is a fine, really fun webinar, and it's good to be here. From the start, thank you for providing me with this actually opportunity. Let me please share my screen first. Yes. Do you have it actually? Or
yes.
no?
Yes, we can see.
Very well.
Thank you.
Yes, thank you. So about all the performance and all the researches that we are conducting in Iran right now, and it's all about masonry school buildings. We are actually talking about masonry buildings in terms of actually schools, because as we can say, and all the efforts that has been conducted in Iran to actually be able to improve and enhance, all things that can we be able to have much more actually durable masonry structures, especially in schools. And I can say that because of the limitation of time, I have to do it more quicker. And I can say that more than 89% of Iranian school buildings are masonry. And in terms of if we decide to talk about the seismic prone areas and just all the buildings, school buildings, we can say that according to code number 2800 of Iranian standard, we can only use confined masonry buildings in terms of school. Right now, actually, I can say that during this past recent years and all the efforts that has been conducted, and all we have done, all these sessions in 2015 for safe schools for all, actually in terms of masonry schools, I can actually announce that we have put so much effort to be able to enhance the performance of masonry school buildings, and just to retrofit buildings, which is which has significant importance, for safety of millions of children right now in Iran. And I can actually say that from recent years, for about 20 years ago, we started all this process. We did very fine things. We I can say that for about the 18 millions of students we have today in Iran, and just so many operational processes was started to retrofit all the buildings. And I can say that in Iran, the only retrofitting technique we can use, because of the limitation of technology, unfortunately, we use actually shotcrete. We apply shotcrete on masonry walls to enhance the performance of the building. And this is all the framework. Right now, I can say that we are evaluating the performance of all those school masonry buildings to see what we have done in recent and in these past years. What all the actually retrofitting operations that have been conducted, have they been actually, I can say that, have they been effective? Have we actually enhanced in performance of our school buildings, and we can provide a safer place for all children to actually enhance themselves and become a really educational man. We have totally worked on two kind of confined masonry buildings. One of our studies, which is about the seismic resilience evaluation of confined masonry school buildings, which is exactly by retrofitting by shotcrete method, is actually under review in Soil Dynamic journal in Elsevier, which has been for about 70 days. And we think we're going to have a really good effort. And as you can see on the left side of my screen, there's some actually incremental dynamic analysis that has been conducted on masonry, masonry building. And it's a comparative situation, which in the above a situation, we have evaluated the building in 2% and 10% hazard levels. And we can see that in 2% and 10% in both hazard levels, the performance of building has increased a lot. Unfortunately, because of the limitation of the time, actually I can provide more valuable details. But this is it. What we have done overall in Iran is to actually the same as we have done in the retrofitting procedure of Adalat school, which is one of our schools in Iran. Again, retrofitting by applying shotcrete, the same as all many schools, to provide a safer place. And just considering all the details and all the complexity that masonry buildings have, just to enhance all these stuff, which is really incredible. I can say that this topic is really important, specifically in Iran, because of the many schools that we have right now, which are overall in actually masonry structures. So
I need to stop
really
you there.
Yes, thank you. Thank you.
Thank you.
Actually, I can say that, yes, very well. Thank you so much. Thank you.
Thank you. Thank you, Mali. So we have now ended up our session on reactors, and I would like Sebastian to join me as we open the open discussion on the way forward regarding standardization, global expansion, and resource and knowledge exchange. The first person that I would like to call on the issue of standardization is Svetlana, as she has some idea for the near future.
Yes, thank you, Dina. So we discussed, as Asana mentioned at the beginning, about this white paper that we are planning to develop based on this event, and the presentations, the findings, some input that we hope to receive from you in the next few days. That in that white paper, one of the aspects, very important aspects, will be to emphasize the deficiency or gaps in the codes and the current codes and standards. So Asana is sharing here the topic of white paper, and I believe that she will share this document with you as well, which are just the ideas. But what we discussed is at the upcoming World Conference, we're going to have a special session on confined masonry. We hope that by that time, that will be end of June, we will have for sure this white paper, and that would be a great opportunity to then share and discuss. So if you have any ideas specifically regarding the code issues and also other issues related to white paper, please share them with Asana, and then we will have them all together. Thank you.
sorry. So Sebastian, I don't know if you want to raise any specific issues that you would like people to react or comment on.
Well, I wanted to ask an open question to all of the presenters and attendees, so everyone really. So moving forward, there are a lot of excellent confined masonry codes out there. Like any codes, they're constantly adapting, we're constantly learning, we constantly have to improve all of the codes around the world. I'm curious how people who are working in countries around the world where confined masonry would be appropriate, what's their preference in terms of codes? Do people want to adapt? Do people want to work on their own research and build their own codes? Do people want to adapt existing codes? And for those who are already where codes exist, how do they want to take that forward, and how easy it is to incorporate research from other areas? For example, let's say one code, there's lots of research happening in the Philippines, how easy it is to incorporate into Mexico. So I'm just curious to see what people on the ground think, who actually potentially have the ability to influence those codes, write those codes and influence them.
Yes, who would like to take the mic first on this quite open question? Sergio, you might like to.
Well, I think the question is have different answers, but I will tell you what will happen in Mexico. We will be open to see what other research is applicable to the types of masonry that we have in our country. In many cases, we have reviewed research, whether numerical, experimental, that pertains to particular units, and they are not available in Mexico. Those conclusions cannot be readily applicable or translated into a code requirement. But when we see that there are similarities on the type of masonry, the type of construction that we have in Mexico, or areas for improvement of the construction practice in Mexico, certainly we do include them in the new regulations that we produce. So we are very open into that.
And Sergio, how can we as a network help out that process? Do you see a lot of overlap in research, or is it sometimes quite hard to find different people research around the world? How can we sort of facilitate this sort of knowledge sharing, I guess?
I think that there is true some overlap in research, but I think that symposiums like this and meetings like we will have in Milan, the network that Svetlana is leading, are the best places to locate the research that is being ongoing, so that we know and we don't repeat ourselves and in terms of the developments that we are carrying. But as you say, the more information that we have available, the better would be to fine-tune the research that we conduct.
I would like to add, if it is okay. So Sebastian, that was excellent question. I think I hear echo. It's okay. Okay. So sorry, we have echo here locally. So what I wanted to say is that Sergio responded nicely to this question, but it is important to emphasize that most countries prefer to have their own research, or the research that is really follows their practices. For example, in Europe, we have Eurocode, and I've been involved in one of the committees related to masonry, but let's say there is limited research on some topics related to confined masonry in Europe, and there was no enough evidence to, let's say, change some provisions because there was no European research going on. And practice in, let's say, Mexico, where there is a great research and very frequent updates of the codes, are somewhat different. So we can learn from the research of others, and I'm strongly in favor, even though I personally don't have too much opportunities to do experimental research on confined masonry, that experimental research is very valuable for improving the codes. And I think more is better. it wouldn't hurt if we have more research, and we identified some topics there where research is particularly scarce, like walls with openings, even this tooting, the question of tooting and interface, and out of plane behavior. And so there are lots of grounds, so there's lots of space for new research, and it is preferable if, at least on a regional level, there is more research in the topics, the areas that where there may be differences in the opinions or the results that we get from numerical simulations and so on. So anyways, that's my, based on experience from the code development, and the same applies to other codes, I would say, for reinforced masonry and others. Thank you. I'm not sure if anybody else would. And I would like to add, actually, that's really interesting, the questions that we had now talking about also the research gaps. Confined masonry, as we discussed and I mentioned at the beginning, and we could see from different presentations, are usually uses masonry elements which are clay bricks or hollow blocks and concrete blocks. But these questions that were posed about, let's say, can it be used in combination with adobe blocks, or can it be used in combination with stone? They're very important, and in fact, there is some evidence that the research has been done. So I think it's important that we also compile these resources for the colleagues from the countries that would like to use. For example, research on adobe. I'm not sure if Daniel Quinn is here. He was one of the presenters, a colleague from Peru. They did the research on confined masonry with adobe and with the stone masonry. I have seen some applications in Algeria, and I'm not sure if they've done research, but actual buildings were constructed. And since Algeria has experienced several earthquakes in the last, let's say, 20 years, so we could post those and contact those colleagues, so that maybe as one of the responses could be that in some of these interested, I'm sure who was asking those questions, but that would be useful because it's really not widely publicized and maybe useful for future research. So that's something to add.
Thank you very much, Svetlana. I think there was Tim with his hand raised, and as I think it's, I'll give you the mic, Tim. I will also ask you a more wider question that maybe you can touch on. Indeed, we have been talking about research, and we have been talking about, let's say, formal confined masonry, or what we think engineered confined masonry is. But as we have heard from several of the speakers, and not least Tim, there is a gray, let's say, area of informal, semi-informal, semi-formal, and formal in terms of the level of engineering that goes into it. In theory, schools should belong to the formal side, but in fact, we found in several countries, and especially in rural area, perhaps, or in non-main urban areas, that they are constructed with local knowledge, but not necessarily with formal technical knowledge. So the issue is, shall we also concentrate the research on that, and shall we actually put our effort in producing guidelines and rules that are aimed at making these buildings safer and bring them into the formal remit, rather than, let's say, over-engineering the confined masonry that we already know as engineered. I know that it might sound a little bit strange, but Tim, please.
I will
slightly provocative.
I will do my best. What I wanted to comment on is this issue about adapting codes and guidelines in various countries, and this was something, I talk about my experience with confined masonry began in Indonesia, And one of the barriers that we ran into right away was the issue of out of plane, because the walls, the research that had been done up until that point and even now, was reflective of how confined masonry is constructed in the countries where the research is done, like Mexico, Peru, and so on, where the walls are thicker, the columns are thick, tie columns are thicker. But in Indonesia, that doesn't work. And so we ran into a significant challenge. You know, the initial thinking when we were looking at this is, oh, those walls, they're not going to work. They're going to fall over because they're too thin, they're too tall. It's just not going to work based upon based upon the research and the experience that had been done to that point. But the performance of these walls in subsequent earthquakes in Indonesia showed that they do work. They do stand up. They don't fall over. You know, what we saw was that when there were out of plane collapses, it was either due to a tsunami crashing into it, or it was due to failure of the tie elements, not the wall itself. That opened up, okay, we have a system here that we've seen work, but we don't have any evidence, we don't have any research, we don't have any codes that can really apply to be able to definitively justify, you know, what we're seeing. And I think, you know, a lot of improvements have been made in that area over the years. But there's still a lot of holes. Out of plane is one of them. It's a particular interest of mine, given that experience in Indonesia. In answer to your question, Dina, about informal versus formal, there is an effort. It's kind of stalled at the moment, but I hope to revive that effort to develop engineering guidelines for confined masonry to make it more formal. I have the draft of that is sitting in my computer right now. I'm still in the process of working on it, I'm hoping to be able to re-engage that effort. And I think a lot of the people in this webinar would be, I would hope to get contributions from some of you. I will be reaching out to some of you to try and reinitiate that effort. And of course, we'll be discussing that in more detail in Milan. But there is going to still be a place for informal construction. There's still going to be a need, because a lot of, you know, having formal guidelines will be great for confined masonry for school construction, because should be formal construction. It should not be informal. But for housing, it's not really practical to have a formal guideline or a formal code that would, most codes don't have any provisions for housing construction, not just for confined masonry, but for any type of construction. So to try and impose something like that would be really, really difficult, and in reality is not going to work. Builders are not going to follow, they're not going to read the codes. They're not going to know. So having an informal, having a practical, guidelines for informal construction, I think there's still a place for that, and it's still important to have that.
Thank you very much, team. And maybe Sebastian, you want to ask the next rounding question?
Yes, again, an open question. I wanted to ask what people see, what people have found the barriers in their various countries to using confined masonry. Have they found lots of barriers in terms of, because it's not yet in the national code, they actually can't use it? Is it guidance available? Is it knowledge on the ground? Is it costs? I'm just curious what barriers there are, so we can, as a network, explore how we can try and work around them.
And please, anybody is welcome to provide answers to this, because we want to go well beyond the people. Yes, I think Ramesh, you've opened your mic. Maybe you want to say something, and then Sophia.
Yeah, so just want to share. Implementing in a individual small scale, there is no problem, because the engineers can explore even the international guidelines and then implement design. But expanding it to the larger scale, and there is the problem, because it requires, I think, three things. The one is sufficient awareness, importance, benefit to the wider level of the stakeholders. So if we don't have the sufficient awareness, it's impossible to go for the larger scale. Second is we have to have the sufficient capacities among the professionals also. So a wider training for the technicalities, designs, and others inspections for the wider, then we can go to the larger scale. And third is to support that through the system. It's not only the code, but the bylaws or other the subsequent standards or the guidelines to promote and to support that. So if we have these all three, then we can go to the larger scale. So in Nepal also, if we want, I think we can construct the confined masonry building without any problem, because the code already have the design parameters. We can design and we can do it. How to promote the larger scale, that's the the problem. I think listening to today, I could not attend yesterday, but even for this retrofitting also the same thing, the retrofitting 5, 10, even 100 is possible through support, arranging, checking and others. But when we start going to the thousands, then we need many of these things together. Thank you.
Thank you very much. Very insightful. And Sophia, please. And in fact, Sophia, I had a special question for you. I wanted to, given your presentation, I just wanted to know how an NGO can mobilize an official national committee elsewhere. And if you can tell us a little bit more about that and the connection with the university and so on, because I think that's a very important loop at national level.
Okay, thank you. Actually, I am at the same time in another meeting that is just starting, but I wanted to stay here for the final thoughts and the comments, because I think that this symposium was so dynamic and we learned about so many topics. So that's why I wanted to stay. So I'm going to be I'm going to say just a few minutes. First, I want to say that the challenges that we are facing right now with the regulations, I think we need more research. I'm talking about in the formal sector, but also in the informal one, that is the one that I work the most. In the informal sector, for example, for us, our main challenges are related with not having enough researchers around, for example, connections between slabs and existing slabs and walls. For example, in Colombia and also in Latin America, it's common to find prefabricated systems in the slab not connected to the walls. So you have walls in the first stop not connected to the slab, and then walls in the second floor not connected to anything. So the risk and the vulnerability is extremely high. So we need more research in different topics. And answering your second question, I think from build change point of view, our mission is to change systems. That is why we cannot only work in the technical aspects. The technical aspects are fundamental, and having the guidelines is just the first step we need, is the basis to start working. But we also have to work with the government at the local and national level to create like the framework in which we can apply this regulation in a country, in a complete country. And we also have to work with the banking sector and looking for how are we going to finance these kind of projects. In some countries, we are using home improvement programs that are subsidized by the government, but in some other countries, they do not exist. And we have to work with microfinance institutions, or maybe we have to also take into account the banking sector and getting all of them involved in the whole process. So it is not easy, but it can be done. And I think it depends on the momentum that we are living right now, I think at least in Latin America and the Caribbean region, engineers, politicians, people in general is talking about informal housing and how we can address the problems and how we can reduce the vulnerability, thinking about risk reduction, but also thinking about making this type of structures resilient to climate change. So we are like involving different topics, and I'm not sure if I answered completely your question.
Thank you very much, Sophia. And there is the hands up by Vaibhav.
Yeah.
Yes, Singer. Yes.
So I can share some experience from India, and I think Professor Brzezic can also better share. So I think to the query of Sebastian, so one of the misconception also is regarding the cost. So many if when we introduce this confined masonry to a builder, so they say that if I have to put so much of reinforcement or the concrete, so why can't go with the reinforced concrete frame? Why the confined masonry is required? But it has been shown, we have shown from the large project which we have done at IIT Gandhinagar, Professor Sudhir Kejan led that construction. And we have shown that the cost is much lower compared to a reinforced concrete frame building. And also one of the thing in adaptability, especially another misconception is that the time of construction, because of the shuttering and all these things. And many countries are not so trained to do this confined masonry. And maybe if some of the good practices which can be adopted from Mexico, Peru, where this confined masonry is quite popular, and some kind of a guidelines can be built, especially on the construction, especially on the shuttering part, that how even for the mass housing, even for the government projects, this confined masonry can be adopted, and the pace of construction can be also managed in a better way. Thank you.
Thank you, Vaibhav. If I may add just a couple of things to build on what Vaibhav said. It is interesting that most of the guidelines that we have for construction are also focusing on single-story buildings. And so when we have to expand it to multi-story buildings, and that is ambition to have, whether it is school or a residential building that is higher, there are no really recommendations which are coming from other countries that have experience. So when the IIT Gandhinagar project was going on, where 4-story buildings were going, we were asking for advice from Mexico. That's how it was, because that was actually exactly a challenge, how to go with the upper floors. And the second thing is, based on Indian experience, where there was no code and the application had to happen, it was the designers and the leaders who were running the project, of course, Professor Jain, were looking into other countries. So that is the best that you can do. And it was possible on that one case. But then later on, of course, code has been evolved and that happened. But first time before the code, you have to look at experience, the best practices of the countries that are well established in terms of application of the technology. I mean, that's I think very obvious choice or strategy, I would say, if possible. Thank you.
Thank you very much, Svetlana and Vaibhav and all. I just, we are slightly over time, but I hope that a few can still stay on, because one element that we haven't discussed much yet is the issue of durability and sustainability, which is actually going to become central if we look at this in terms of net zero and carbon footprint. We heard this morning from Sergio, for instance, that alternative material can be used for strengthening and retrofitting from plastics material to natural material and so on. We have had, although we have not explicitly spoken about it, but we had quite a number of queries relating to dried bricks, and therefore with bricks and units with a lower carbon footprint than traditional kilned bricks. With stabilized materials, for instance. So I would like, and on the other end, we have heard about the issues of corrosions, the issue about durability of the material. I think that there was a specific question on efflorescence that was raised earlier, to which maybe we have not provided an answer. And I just would like to have a few minutes of, and of course, we heard from Anna about the, how we can quantify the carbon footprint. I have two queries here. First of all, how do we bring the alternative materials into the confined masonry knowledge and technology that we know, and therefore how in areas where confined masonry has not yet been popularized, shall we try to do this considering the new materials rather than, or considering alternative materials as well as more traditional one. This is one aspect of it. The second aspect, we have, when we are talking about the carbon footprint, in the carbon footprint counters and methods of counting carbon footprint relate very much to the, let's say, building industry as it is currently operating in developed countries rather than in developing country, where some of the processes actually might have very different weight on the carbon footprint counts. So I would like to explore these two aspects of it, if anybody would like to provide any feedback. Sebastian, maybe yourself, given your experience with natural materials, you might
yes,
venture to break the ice.
I can try to give some thoughts. I think on specifically on cement stabilized earth, I think we could probably infer the results from existing tests, because the cement stabilized earth, I'm thinking compressed earth stabilized blocks, they can have a similar strength to a fired clay brick, low fired clay bricks, 2, 3, 4 MPa, which means their behavior is likely to be very similar. So if there is existing testing using a lowish strength fired clay brick, the results of that should be, we can infer the results of a cement stabilized confined masonry wall with a similar strength of mortar and brick. Obviously, we should do testing to verify that, but I think we've got probably reasonable confidence with that. It's probably worth doing an embodied carbon assessment, because although cement stabilized earth bricks are generally lower carbon, they may not be as lower carbon as we want because of the cement content. So sometimes these lower carbon materials aren't as lower carbon as we want. So we need to be honest about that. And there might be higher durability requirements, or they might not last as long. But they're definitely worth exploring.
And what about alternative reinforcement? Stop using steel.
So, for example, galvanized or stainless steel,
or no steel at all. So we're using reinforced plastic or FRP bars, or.
I can give some initial. I can try and break the ice with some initial thoughts. I think they need to have a similar performance to steel. So we know steel is very ductile. That's the advantage. We know that FRP bars are typically very brittle. Exactly. That's the risk there. If there are alternatives to steel reinforcements that have similar ductility, great. There's a lot of ductility happening in confined masonry systems, so we do need that. So I'm not sure how many alternatives there are available at the moment. Steel may be the best. Actually, on a confined masonry building, the steel doesn't contribute most to the embodied carbon. It's the concrete and it's the fired clay bricks. Those are the areas to focus on, really. So reducing your concrete quantity certainly helps, and looking at alternatives for the fired clay brick and trying to pick things which are lower carbon helps, while thinking, obviously, maintaining your performance and maintaining your durability.
Thank you. Thank you very much, Sebastian. Any other comments on this? In which case, I think there is a hand raised by Jamal Ilayan. I think very kindly stayed on for a long time, so we'll give him the microphone. Jamal, if you would like to ask your question. Or maybe he has left already, leaving his hands on. Jamal? No, it's not there. So then in this case, because we have already gone over time, I would just like to close the sessions and close the symposium. I would like to thank again all the speakers, the reactors, the participants for a very dynamic and interesting 2 days of presentation and discussions. If you are there and you can switch on your camera, we will take a few snaps to circulate, and please feel free to circulate emails and so on, and popularize the event. And one more thing that Hassan has asked me to remind you is about the white paper that we want to bring together. Please, she will be quite insistent in getting your feedback in the next couple of weeks. So bear with her, but at the same time, please, until, now that all the ideas are fresh, is the best time to bring them together. And you will be rewarded by receiving the first draft feedback compiled as soon as possible as well. So we hope to have all of this wrapped up in the very near future, let's say the next few weeks. But I would like to thank you all, especially our colleagues in the East and the extreme and the West, because they had to endure either late night or very early morning. But I think it was very important to bring everybody together on the same screen. And we really sincerely hope to continue these conversations. For the one of you that plan to attend a World Conference of Earthquake Engineering in Milan, certainly, but for the others, we will have follows up. I don't know if we have the resources to organize another similar webinar soon, but we certainly follow up with other events where we will continue this conversation. Thank you again, everybody. Thank you, Sebastian, for co-hosting this last part of the debate, and goodbye to everybody.
Bye.
Thank you all. Bye-bye.
Bye-bye. Thank you.